Light takes time to travel. When you look at something 1 mile away, you're seeing it as it was 5 microseconds ago. Look at the moon, and you're witnessing light that left 1.3 seconds in the past. Gaze at the nearest star, and you're staring at photons that began their journey 4 years before today. This is confirmed science. Every photon crossing the cosmos carries a frozen image of the moment it was born. And right now, the James Webb Telescope, sitting 1 million miles from Earth, staring into the darkness, is catching photons that have been traveling for nearly the entire history of existence. Its mirror stretches 21 feet across, coated in gold to catch infrared light. Infrared is what remains after the universe's expansion has stretched visible light beyond recognition. Think of it like a siren passing you on the highway. The sound drops lower as distance grows. Light does the same thing across cosmic distances. The universe itself is a medium that transforms light, stretches it, ages it, redshifts it. Webb isn't just looking far away, it's looking backward through time itself. The most distant galaxy it found emitted its light 13.5 billion years ago. We're seeing this galaxy as it appeared when the universe was only 290 million years old. To put that in perspective, if the universe's entire age was compressed into a single year, this galaxy formed on January 2nd. Here's what makes this extraordinary. When that light began its journey, Earth didn't exist. Our sun hadn't formed. The Milky Way was still assembling itself from cosmic gas. Dinosaurs came and went. Humans rose and fell. Civilizations bloomed and crumbled. All of it happened while these photons crossed the void. Every image Webb captures is a fossil, a preserved moment, frozen in light. The telescope gathered photons for almost 10 hours to capture one ancient galaxy. 10 hours of collecting light that has been traveling for 13.5 billion years. The patience required is staggering. Scientists used an instrument called a spectrograph to confirm the distance. This device splits light into its component colors, like a prism creating a rainbow. Specific patterns in that rainbow reveal how fast the universe has been expanding since the light was emitted. The farther away something is, the more its light has been stretched. This galaxy showed a redshift of 14.32, the highest ever recorded for a confirmed galaxy. But here's where things get strange. In October 2023, scientists spotted an object they named Galaxies 14-0. Then they spent months doubting what they saw, because it appeared too bright, too large, too developed, too mature for something that shouldn't exist yet. When astronomers pointed Webb's spectrograph at this galaxy in January 2024, they confirmed their suspicions. The object sits 13.5 billion light-years away. It formed just 290 million years after the Big Bang. That puts it in an era called Cosmic Dawn, when the first stars were supposed to be flickering into existence. Emphasis on supposed to be, because this galaxy measures over 1,600 light-years across. This is a fully formed, massive structure, a giant. And according to our current models of how galaxies form, it should have taken billions of years to assemble something this large. It didn't have billions of years. It had 290 million. That's like walking into a hospital and finding a teenager who's already finished medical school. It shouldn't be possible. And yet, there it is. This discovery shattered what we thought we understood about the early universe, about how fast galaxies could grow, about how quickly structures could assemble themselves from the primordial chaos. The James Webb Telescope didn't just look deeper into space. It revealed that our timeline for cosmic history might be fundamentally wrong. We're not just observing distant objects. We're witnessing the universe's childhood. We're seeing the first structures that would eventually lead to everything we know. Every star, every planet, every atom in your body can trace its origin back to these early moments. The universe, it turns out, built itself far faster than we ever imagined. It's impossibly small compared to modern galaxies, but for its age, it's a giant. This object contains several 100 million times the mass of our sun, all crammed into young blazing stars. Spectral analysis proved it. Pure starlight. Newborn stars screaming with ultraviolet radiation. But here's the problem. Theory said early galaxies should be small, dim, simple. Just a few million stars scattered across the darkness. The universe, at 290 million years old, shouldn't have had time to build anything substantial. Gravity doesn't work fast. Gas collapses slowly. Stars take millions of years to ignite. Dark matter, halos need time, vast stretches of time, to accumulate enough material to even seed a galaxy. And yet, there it was, bright enough that the James Webb Space Telescope could see it, even if it were 10 times fainter. That terrifies astronomers. Because one galaxy this old, this massive, this bright, doesn't mean it's alone. If one exists at this distance, dozens more are probably hiding in regions Webb hasn't even looked at yet. The team didn't have to wait long to find out. They discovered a second galaxy, J, A, D, E, INS, G, IS, Z, 14-1. Nearly as distant, nearly as impossible. Two record-breaking galaxies in the same field of view, both contradicting everything the models predicted, both producing starlight at rates that shouldn't be possible. But what really unsettled researchers was what they found inside. Spectral lines revealed more than just hydrogen and helium, carbon, oxygen, nitrogen, heavy elements. And here's the thing. Those atoms only form inside stars. They only spread through space when those stars explode, which means an earlier generation of stars already lived and died before this galaxy even existed. The timeline keeps getting pushed backward. One astronomer described the feeling perfectly. It's like excavating a smartphone among ancient Roman ruins. The technology is too advanced for its era, the structure too sophisticated, the brightness too intense. This discovery forced scientists to extend humanity's window into the cosmic past by 40%. 40% deeper into time than we'd ever seen before. And the question haunting everyone is this. If galaxies this massive existed this early, what else are we missing? Here's where the universe stops making intuitive sense. Light travels at 186,000 miles per second. Nothing moves faster. Every measurement we've ever taken confirms this. In 1 year, light covers about 6 trillion miles. Multiply that by the universe's age, 13.8 billion years, and you get how far light can travel since the Big Bang. The answer should be 13.8 billion light years. Simple math. Except it's completely wrong. The actual edge of the observable universe sits 46.5 billion light years away in every direction. The total diameter spans 93 billion light years across. We live inside a sphere of space nearly 7 times wider than the distance light could possibly travel in the universe's entire lifetime. This isn't a mistake. It's not a flaw in our calculations. It's expansion. Space itself is stretching. Picture this. You draw dots on a balloon, then inflate it. The dots move apart without traveling across the balloon's surface. The space between them is growing. The universe works the same way. Galaxies aren't flying through space. Space is carrying them apart. When that distant galaxy emitted light 13.5 billion years ago, It was much closer to us. Much closer. But as its light traveled toward us, the galaxy never stopped moving away. By the time that ancient light reached our telescopes, the galaxy had drifted to a current distance of 46 billion light-years. Think of it like this. You're running on a treadmill toward someone standing ahead. You run forward, but the treadmill pulls you backward. You might eventually reach them, but they'll be farther away than when you started. Light does the same thing, fighting against cosmic expansion the entire journey. And here's what makes this deeply strange. Regions of the universe exist beyond 46.5 billion light-years. They exist right now, somewhere out there, beyond our cosmic horizon. We simply can't see them. Their light hasn't reached us yet. Maybe it never will. Because space doesn't just expand, it accelerates. The treadmill keeps speeding up. Imagine staring at the night sky and thinking you've seen everything. You haven't. Not even close. We know something lies beyond our cosmic horizon. Something we can never see. Space expands infinitely in all directions, but light takes time to travel. The observable universe is just the bubble around us where that light has managed to reach. Beyond that boundary, billions of galaxies still shine. Stars still explode. Planets still orbit. But they exist in a region of space so distant that their light will never find us. We're trapped inside our own sphere of visibility, watching it slowly grow. But here's the thing. The boundary isn't moving fast enough. In the 1990s, astronomers discovered something that shattered our understanding of the cosmos. Distant supernova, exploding stars at the edge of creation, were dimmer than expected. The universe wasn't just expanding, it was accelerating, speeding up, and something was pushing it. Scientists called it dark energy, and we have no idea what it is. What we do know is this. Dark energy makes up 68% of everything that exists. It fills the entire universe. And as space expands, dark energy doesn't get diluted. Its density stays constant, which means as the universe grows, there's more dark energy everywhere, pushing even harder. The expansion rate isn't slowing down, it's getting faster. Every second, distant galaxies slip further away from us. Every second, they cross a point beyond which their light can never reach Earth. We're losing galaxies to the accelerating expansion of space itself, and we never even knew they were there. Then came the James Webb Space Telescope. Astronomers pointed it at a tiny patch of sky, a region barely larger than 3 full moons. They let it stare. For 250 hours straight. The Hubble Space Telescope had examined the same sliver of space years earlier and found roughly 10,000 galaxies. The scientific community thought that was complete. A comprehensive map of the deep universe. They were wrong by a factor of 80. When Webb's images came back, scientists counted 797,942 galaxies in that single frame. Nearly 800,000 distinct collections of stars, each one containing billions, some containing trillions of stellar masses. To grasp the scale, imagine printing the famous Hubble Ultra-Deep Field photograph, one of the most iconic images ever captured, on a standard sheet of paper. The Webb image would need to be printed 13 feet tall and 13 feet wide at identical detail to show everything Webb saw. A wall-sized mural of cosmic history compressed into one photograph. But the numbers weren't the real revelation. Look at how those galaxies are arranged. They're not scattered randomly across space like dust motes in air. They cluster. They form threads. They gather at intersections like a cosmic web. And there are empty regions, vast voids where almost nothing exists. This pattern reveals something profound. The universe has structure at the largest scales. Dark matter filaments weave through space like the strands of a cosmic spiderweb, connecting every major mass concentration in the universe. Webb's real superpower lies in its infrared vision. It doesn't just see visible light like our eyes. It pierces through cosmic dust, the thick clouds that have hidden entire populations of galaxies from every telescope before it. In infrared, what appears empty blazes with activity. Dusty regions where new stars are being born right now. Ancient galaxies whose light has been stretched by the expansion of space into wavelengths our eyes can't detect. Galaxies that Hubble, the most powerful telescope of its era, literally couldn't see. To make sense of 800,000 galaxies, the team had to invent new methods. They measured the brightness of each galaxy. They classified their shapes. They calculated redshifts to determine distances. They estimated masses and ages. The process took years. The result is one of the highest quality datasets in the history of astronomy. And then something extraordinary happened. The researchers released everything: the raw images, the measurements, the entire catalog, an interactive viewer where anyone on Earth can search for specific galaxies or explore random patches of deep space. They democratized the cosmos. Before Webb, that data would have been locked away in academic institutions for years. Now, a teenager with a computer can access the same information as the world's leading astronomers. Amateur scientists worldwide are now mining this data for discoveries we haven't even imagined yet. But perhaps the most stunning revelation is what Webb found that shouldn't be there. Before the telescope launched, astronomers made predictions. Based on decades of data, they estimated how many galaxies should exist at extreme distances. Galaxies that formed when the universe was less than 500 million years old, when everything was chaos and confusion and the first structures were just beginning to form. They predicted Webb would find perhaps a few dozen of these ancient galaxies in a survey this size. Webb found several hundred, 10 times more than expected, which means the universe formed galaxies far faster than our theories predicted. It means our models of how galaxies begin are incomplete. It means the early universe was far more complex, far more fertile with creation than we ever imagined. And we're only beginning to understand why. Every image Webb sends back rewrites the cosmic story. Every pixel contains billions of years of light that's traveled across the universe to reach our cameras. And somewhere out there, beyond the edge of what we can observe, that story continues. Galaxies we'll never see. Universes of experience unfolding in the dark. The cosmos is so much larger, so much richer, so much stranger than we ever thought, and we've just turned on the lights. Imagine you're looking at a newborn baby, just a few days old, and you find them standing upright, speaking fluent sentences and solving calculus problems. That's essentially what we're seeing in the deepest reaches of the cosmos. 13.8 billion years ago, the Big Bang happened. We know this with certainty. Multiple independent measurements all confirm it. What came next should have been simple. A smooth, nearly uniform universe. Tiny density ripples existed, sure, but matter was spread evenly throughout space. And then gravity did what gravity does. It amplified those tiny ripples into clumps. Over millions of years, those clumps became stars. Those stars became galaxies. The process was supposed to be slow, predictable, gradual. The math was clear. Scientists could calculate exactly how many galaxies should exist at any given cosmic age. They knew how long gas needed to cool. They understood how long dark matter halos took to accumulate mass. They factored in the time required for stars to ignite and forge the heavy elements that seed future star formation. Every step took millions of years. Then the James Webb Space Telescope looked back at the early universe, and everything broke. Webb found 10 times more galaxies than the models allowed. 10 times, not a slight discrepancy. A 10-fold explosion of galaxies crowding into a cosmic era that should have been nearly empty. Researchers checked their instruments obsessively. They verified measurements. They hunted for errors in the data. Everything confirmed the same impossible result. Within just 500 million years after the Big Bang, the universe was teeming with galaxies. Bright galaxies. Massive galaxies. Galaxies containing billions of times the mass of our sun. The universe was producing too much light too early. Think about the challenge. You have 400 million years to build structures containing 1 billion times the mass of our star. We don't know how to do that with current physics. We don't know how matter could behave that way. Maybe stars formed more efficiently back then. Perhaps the denser cosmos allowed gas to collapse faster, or gravity worked differently when space was more compressed. Perhaps environmental conditions allowed star formation to proceed at rates impossible today. But these are guesses. Educated guesses, yes, but guesses nonetheless. The observations are real. The explanations remain uncertain. Then there's dark matter. Different models predict different abundances of dark matter halos in the early universe. If dark matter behaves differently than we assume, it could create the exact conditions needed to accelerate galaxy formation. Webb's measurements might finally reveal which theories are right and which ones are fatally wrong. But what troubles astronomers most isn't a single anomaly. It's consistency. The surprise repeats itself again and again. Multiple surveys, different regions of sky, different instruments. Every deep field Webb examines tells the same story. Far more galaxies than should exist. The implications cascade outward like dominoes. If galaxies form this abundantly, they must have influenced their surroundings earlier than expected. They would have begun reionizing the universe sooner, flooding it with light. They would have enriched space with heavy elements faster. They would have seeded the formation of larger cosmic structures earlier. The entire timeline of cosmic evolution might need rewriting. Every textbook chapter on the early universe might be incomplete. And then astronomers found something even more disturbing. Galaxies so massive they border on impossible. Objects appearing in the infant universe weighing 100 times more than theory permits. The discoveries were so shocking that researchers initially called them universe breakers, because their existence seemed to violate the fundamental laws of cosmology itself. Here's why this matters. Building a massive galaxy takes time. Dark matter must collapse into a halo first. Ordinary matter must then fall into that halo. You're assembling something incomprehensibly vast from the raw material of space itself. There's a speed limit. There's a timeline. You can't skip steps, except apparently you can. The universe did it anyway. Picture the cosmos in its infancy. Gas cools and fragments. Stars ignite. Those stars burn out and die, but not before forging the heavy elements that seed the next generation. This cycle repeats over and over as galaxies grow. It's elegant. It's predictable. It's written into the laws of physics itself. But here's the problem. The early universe didn't follow the script. Each step in this cosmic dance has a hard limit. You can't compress gas faster than the speed of sound. Push harder, and you create shock waves that heat everything back up, stopping the process cold. You can't form stars instantly. You can't skip the billions of years that stellar evolution demands. The math is unforgiving. Plug in the age of the early universe, run the calculations, and you get a precise answer. Galaxies can only be so massive at any given point in cosmic history. Then astronomers looked through the James Webb Space Telescope and saw galaxies that shouldn't exist. Some of these early galaxies were 10 to 100 times more massive than the physics allowed. Their brightness spoke of stellar populations too vast, too numerous, for the cosmic era in which they formed. It was as if someone had violently compressed the entire history of galaxy formation into a fraction of the time available. Scientists scrambled for explanations. Maybe the galaxies weren't as massive as they appeared. Maybe something was making them look bigger than they really were. That something, it turned out, was lurking at their centers. Supermassive black holes, monsters so dense and so ravenous that they blazed with the light of billions of stars. When astronomers accounted for these brilliant cores, the numbers improved. The galaxies shrank to more plausible sizes, still massive for their age, but no longer catastrophic violations of cosmic law. Yet even with those corrections, the problem persisted, just quieter. Roughly twice as many massive galaxies existed in the early universe as models predicted. The discrepancy had narrowed from a factor of 100 down to a factor of 2, but it hadn't vanished. Something remained fundamentally wrong with our understanding. So astronomers did what they always do when faced with a mystery. They looked back at older data. The Hubble Space Telescope had been watching the cosmos for decades, building a careful inventory of galaxies across different cosmic eras. If the standard model was correct, Webb's observations should match Hubble's findings. Same distribution of galaxy masses, same patterns. Any extra galaxies Webb detected should be faint ones that Hubble simply missed. Instead, Webb revealed far more bright, massive galaxies than Hubble's data suggested should exist at all. This wasn't a small discrepancy. This was a red flag. Either the early universe operated under fundamentally different physical conditions than we thought, or our understanding of how matter converts into stars was deeply incomplete. Neither option was comforting, but the mystery only deepened when astronomers turned their attention to what lived inside these impossible galaxies. Meet G NZ11, one of the most distant galaxies ever observed. At its heart sits a supermassive black hole. Not just any black hole, a monster weighing millions, possibly billions of times more than our sun. And here's the kicker. This black hole existed when the universe was only 430 million years old. That should be impossible. Not improbable. Not unlikely. Physically impossible. Black holes form when the most massive stars collapse at the end of their lives. A star needs to be at least 20 times heavier than our sun to create one. When it does, the resulting black hole typically weighs just 10 to 100 times what our sun weighs. From there, it can grow by devouring gas, dust, and entire stars. But this is a slow process. Gradual accumulation, billions of years to climb from stellar mass to supermassive. 430 million years isn't enough time, even if a black hole formed immediately after the Big Bang itself and consumed material continuously at the theoretical maximum rate, an absolute physical limit imposed by the laws of relativity. It still couldn't grow to billions of solar masses by this early date. The universe simply hadn't existed long enough. Yet there it was, waiting, ancient, defying explanation. These aren't abstract puzzles for mathematicians to ponder in quiet offices. They're evidence that something fundamental about how the universe works remains hidden from us. Something about the first billion years of cosmic history doesn't match what our best theories predict. The early universe forged galaxies faster than it should have. It grew black holes larger than it could have. The rules we thought we understood don't seem to apply. Each new observation from Webb tightens the constraints. Each measurement narrows the range of possible explanations. But the core mystery remains. Massive structures appeared earlier than expected. And at the centers of some of these galaxies lurk monsters even more perplexing than the galaxies themselves. The research continues, and somewhere in the data we've yet to collect, the answer waits. An answer that might rewrite everything we know about how the universe came to be. Picture this. The universe is only a few 100 million years old. Darkness still dominates the cosmos. And yet, lurking at the hearts of galaxies, something impossible is already there. Something massive. Something that shouldn't exist yet. The James Webb Space Telescope turned its infrared gaze toward the early universe and found them. Supermassive black holes. Not small ones. Not the kind that take billions of years to assemble. These monsters are already fully grown, already dominating their galaxies, already reshaping the very fabric of space and time around them. And here's the problem. They shouldn't be here yet. Webb detected the telltale signs of one actively feeding. Surrounding the black hole lay an extremely dense fog of gas, spiraling inward at tremendous rates. The spectral analysis was unmistakable. This was a black hole in the middle of a feast, pulling matter down into oblivion at speeds that defy our understanding of how fast accretion should work. The light signatures matched only one thing: a supermassive black hole, far more massive than our Milky Way's own central giant. But Webb didn't find just one. It found multiple, some even more massive than physics suggested they should be, given how little time the universe had aged. This is the crisis at the heart of modern cosmology. How did these objects grow so large so quickly? The first answer sounds like science fiction. What if the black holes didn't start as black holes at all? What if they began as something far stranger? Dark stars. These theoretical objects would be powered not by nuclear fusion like normal stars, but by dark matter annihilation. Imagine a star made of something we can barely detect, burning with the energy of 1 trillion thermonuclear reactors. A dark star could balloon to millions of times the mass of our sun before the dark matter fuel ran out, and the whole structure collapsed directly into a massive black hole. That would give black holes an enormous head start on growth, already birthed into existence at weights that normally take billions of years to accumulate. But there's another possibility, and it's even more radical. In the ultra-dense early universe, gas clouds didn't always need to form stars first. Sometimes, under exactly the right conditions, a cloud containing 100,000 stellar masses could skip the star stage entirely. It could compress, collapse, and transform directly into a black hole of equivalent mass. Just like that. No intermediate steps, no warning. The mathematics works. Our models say it's theoretically possible. We've simply never seen it happen. A third theory involves something we know does happen: collisions. Webb and gravitational wave detectors have confirmed that black holes merge. They slam into each other and combine. Perhaps in the crowded, violent early universe, black hole mergers occurred far more frequently than they do today. Smaller black holes colliding and merging repeatedly could build up to supermassive sizes faster than accretion alone would allow. But here's what makes this mystery truly profound. These black holes matter. They're not passive residents of galactic centers. As matter spirals inward toward their event horizons, the friction heats that material to billions of degrees. The radiation explodes outward, blasting the surrounding gas with energy. This radiation can either ignite star formation across an entire galaxy or snuff it out completely. Supermassive black holes are cosmic regulators. They control whether galaxies bloom or wither. Finding them so early means they shaped cosmic evolution from nearly the beginning. Their influence ripples through the history of the universe itself, but Webb discovered something even stranger, hiding in that same epoch of cosmic history. A galaxy designated GS 3073 revealed an impossible chemical signature. Its light contained nitrogen and oxygen in a ratio that shouldn't exist. The numbers were 0.46, wildly imbalanced for any normal population of stars. Normal stellar nuclear fusion doesn't produce that. Stellar explosions don't create it. And yet, theoretical physicists had predicted exactly this signature from stars that had never been observed, stars that had only ever existed in mathematics. Population 3 stars, the first generation of stars ever born. When the universe was young, truly young, the cosmos contained nothing but hydrogen and helium, no carbon, no oxygen, no iron, no heavy elements to be found anywhere. Stars forming in that pristine environment would be fundamentally different from stars today. Without heavy elements to help cool collapsing gas clouds, those clouds would contract into something monstrous. Not stars the size of our sun, not even stars 100 times more massive. We're talking about monsters. Stars 1,000 to 10,000 times more massive than our own. A star that massive would burn like nothing we've ever seen. Its core temperature would reach incomprehensible heights. Helium would fuse into carbon at rates that seem almost violent. But here's the crucial detail: that carbon would then capture more helium nuclei through a process called the carbon-nitrogen-oxygen cycle. The result? Tremendous quantities of nitrogen manufactured in that roaring furnace. These monster stars would have burned brilliantly but briefly, only a few million years. A cosmic blink of an eye. When their fuel exhausted, they wouldn't explode like supernovae. They would collapse directly into black holes. But during their short lifespans, stellar winds would blast nitrogen-rich material into space. Seeds scattered across the universe. That material, that chemical fingerprint, is what Webb detected in GS 3073. Nitrogen created billions of years ago in the furnaces of stars that have been dead almost as long as the universe has been old. We're seeing the ghosts of the universe's earliest monsters. Stars of legend burning in the primordial darkness. And these ghosts are telling us a story we're still learning to read. Imagine the universe's first stars, monsters on a scale almost impossible to comprehend. These weren't just big, they were monumentally massive. And when they died, they left behind something extraordinary: nitrogen. This nitrogen didn't disappear. It mixed with later generations of stars, creating a chemical signature that astronomers had hunted for decades. When the James Webb Space Telescope finally spotted it, something remarkable became clear. Population 3 stars, theoretical ghosts that existed only in equations and computer models, were real. They had actually existed. For decades, physicists knew these stars should exist. The math demanded it. But math isn't evidence. Not until you find them. Webb found them. And that changed everything. These monster stars solved a cosmic mystery that had haunted astronomers for years: the supermassive black hole problem. Here's the puzzle. In the centers of galaxies, black holes sit weighing millions, sometimes billions of times more than our sun. But where did they come from? How did they grow so fast? The answer? Monster stars. When a star massive enough collapses, It becomes a black hole. Not just any black hole, but one weighing thousands or tens of thousands of stellar masses. A black hole with a massive head start. From there, growth becomes inevitable. Feed it material, and it becomes supermassive, fast. But their impact didn't stop there. These ancient giants flooded the early universe with ultraviolet radiation so intense it did something that seems impossible. It transformed the cosmos itself. The early universe was opaque, a thick fog of hydrogen gas that light couldn't pass through. Then these monster stars switched on, and their radiation stripped electrons from atoms across vast cosmic distances. The fog cleared. The universe became transparent. Rionization, the transformation from opaque to transparent, wasn't gradual. It was violent. It was transformative. And monster stars were the architects. And there's more. Every atom of carbon, oxygen, and nitrogen in the early universe came from inside these stars. In the furnaces of their cores, fusion created elements that had never existed before. Monster stars forged these heavier elements faster and in greater quantities than normal stars ever could. They seeded subsequent generations. They made planets possible. They made life possible. These brief, brilliant giants, burning at the universe's beginning, not now, were essential architects of everything that followed. But even these cosmic titans were just individual objects. They were actors in a larger drama. The universe's true scale reveals itself not in single stars, but in something far more vast. Galaxies don't scatter randomly through space. They cluster. They gather. They form patterns. Imagine filaments of dark matter stretching tens of millions of light years across space, some stretching hundreds of millions. These threads connect at massive nodes where thousands of galaxies pile up like cosmic intersections. Between the threads, voids, enormous empty regions where almost nothing exists. This pattern is the cosmic web. It's the largest structure in the universe. Confirmed, mapped, and confirmed again. How did this web form? Picture the early universe, less than 1 billion years old. Space wasn't perfectly uniform. Some regions were slightly denser than others, infinitesimal variations, like ripples on water. But gravity cares about those ripples. Denser regions pull in more matter. More matter increases gravity. Gravity pulls in even more. The process cascades. Billions of years pass, and those tiny ripples become mountains. Those mountains become superclusters. Think of it like water flowing downhill into valleys. The valleys are regions of concentrated dark matter. The streams are filaments where material flows from one concentration to another. Over cosmic time, these streams become highways, gravitational corridors where galaxies travel, drawn inexorably toward the densest regions. Dark matter is the architect of this structure. It comprises 85% of all matter in the universe. We've never seen it. It doesn't emit light. It doesn't interact with electromagnetic radiation. We know it exists only through its gravity, through the way it bends the paths of galaxies and light itself. Where dark matter concentrates, normal matter follows, like iron filings drawn to a magnet. Scientists mapped the cosmic web by surveying millions of galaxies, measuring their positions in three-dimensional space. Patterns emerged instantly. Galaxies line up along specific directions. They cluster at nodes where multiple filaments meet. They avoid the regions between filaments. The distribution tells a story. The story of dark matter's invisible hand, shaping the universe's largest structures. Everything connects. Every galaxy lives somewhere on the web's threads. The cosmic web pervades the entire observable universe, binding all gravitationally bound structures into one interconnected network. From monster stars forging the first heavy elements to the cosmic web, binding galaxies across billions of light years, each discovery reveals a universe far more connected, far more structured, and far more astonishing than we ever imagined. Imagine our galaxy, the Milky Way, suspended on an invisible thread. That thread connects us to Andromeda and weaves through space like a fiber in an enormous cosmic tapestry. This thread, a filament of galaxies and dark matter, stretches across 110 million light years, linking the Fornax cluster to the Virgo cluster. And here's the thing that should make you pause. The light from the far end of this filament began its journey when dinosaurs were still walking on Earth. The universe isn't randomly scattered. It has structure, and that structure has nodes, places where threads intersect. These are galaxy clusters, the most massive objects ever bound together by gravity. A single cluster might contain 1,000 galaxies packed together, weighing as much as 100,000 billion suns. These nodes are where the action happens. Galaxies that start out alone drift along the cosmic threads like travelers following an ancient trade route. And as they drift, they collide. They merge. The plasma filling the space between them strips away their gas like wind, shearing off a comet's tail. Spiral galaxies transform into elliptical ones, reshaped by the cosmic collision. For decades, astronomers had a problem. The math predicted that dark matter should line these filaments, pooling along the threads just like water following a riverbed. But no one had ever seen it. Then everything changed. Using a technique called gravitational lensing, watching how light from distant objects bends around invisible masses, scientists finally detected dark matter hanging directly on the cosmic web's threads. The invisible skeleton of the universe became visible, and the predictions held up. But then the James Webb Space Telescope found something that shouldn't exist. Astronomers discovered a chain of at least 20 galaxies, closely packed together, swooping through space in a bow shape. They call it the cosmic vine. It stretches more than 13 million light years long and roughly 650,000 light years wide. To put that in perspective, our entire Milky Way is only 100,000 light years across. The cosmic vine is 13 times longer, and all 20 of its galaxies were born when the universe was only a few billion years old. Their light took between 11 and 12 billion years to reach us. Here's why this discovery is so profound. The cosmic vine shouldn't be there. It's too big. It's too organized. It's too mature for its time. The universe wasn't old enough to assemble something this massive. Astronomers estimate the vine's mass at roughly 260 billion suns. That's already colossal. But it's not finished. It's still growing. Galaxies continue drifting along its filament, pulled by gravity. Over the next several billion years, these galaxies will merge and compress into a single galaxy cluster, one of the universe's most massive structures. But here's where it gets truly strange. The two largest galaxies in the cosmic vine have stopped making stars completely. When scientists analyzed the light these galaxies emit, they found almost no evidence of new star formation. The galaxies are what astronomers call quiescent, dormant. They've run out of fuel. And in the early universe, this is bizarre. Most galaxies this old should still be furiously building new stars. Finding galaxies that have already exhausted their gas reserves this early suggests something violent and catastrophic happened. The leading theory: these two giants recently collided. When massive galaxies smash together, they trigger an explosion of star formation that burns through their gas in just a few million years. The collision heats the remaining gas to such extreme temperatures that it can't collapse into new stars. Some of it gets blasted entirely out of the galaxy, flung into space by the raw energy of impact. The cosmic vine is a galaxy structure in the process of being born, but its largest members are already aging. It's a contradiction wrapped in mystery, hanging on the threads of the cosmic web. And it's forcing astronomers to reconsider everything they thought they knew about how fast the universe could build. Picture this: a galaxy full of stars, gleaming across the cosmos. But look closer, and it's a graveyard of sorts. The raw materials needed to build new stars have vanished. The construction has stopped. But why? There's a culprit lurking in the cosmic neighborhood, and it's absolutely brutal. When galaxies live close together, packed into dense cosmic structures, they don't experience a peaceful existence. They swim through oceans of superheated plasma, the blazing hot gas that fills the spaces between galaxies. And this plasma is a killer. It strips away a galaxy's gas through something called ram pressure stripping. Picture your hand thrust out a car window at highway speed. The air resistance doesn't gently push back. It hammers your hand backward with overwhelming force. Now imagine that same physics playing out on a galactic scale. Gas clouds get torn away. Star formation grinds to a halt. A vibrant, active galaxy dies. These cosmic environments hide something even more profound. They reveal unexpected structure. Vast, dense concentrations of galaxies forming far faster than our theories say they should. Webb, the James Webb Space Telescope, keeps discovering these cosmic behemoths. Each one challenges everything we thought we knew about how the early universe assembled itself. Now here's where it gets revolutionary. A team of astronomers has just done something extraordinary. They've cataloged the largest, deepest survey of galaxy groups ever created. 1,678 galaxy groups and protoclusters, stretching back 12 billion years, nearly to the beginning of the universe itself. Think of these groups as neighborhoods in the cosmic web. Each one is a gravitationally bound community, smaller than massive galaxy clusters, but larger than individual galaxies. They're families of galaxies, held together by the invisible grip of gravity, maintaining their own local identity within a far grander cosmic structure. But until now, we've never been able to truly see them evolve. Previous telescopes glimpsed only fragments. Maybe they caught a galaxy group at one moment in cosmic time, then another at a different era. But they couldn't trace the journey, the continuous transformation across billions of years. Webb changed everything. Its infrared eyes are absurdly powerful. It detects galaxies 1 billion times fainter than what human vision can perceive. Through this lens, the evolution of galaxy groups unfolds like a cosmic narrative written in light. In the early universe, these groups were wild, chaotic. Galaxies twisted into irregular shapes, as if still being pulled and molded by cosmic forces. Star formation exploded. Brilliant, violent, unrestrained. The structures were loose, still assembling, not yet solidified into anything stable. But as time moved forward, something remarkable happened. The chaos transformed into order. Galaxies developed elegant, symmetrical shapes, beautiful spirals, graceful ellipses. Star formation slowed, quenched, astronomers call it. The groups themselves became tighter, more compact, as gravity pulled their members closer together. Eventually, many of these groups collided and merged into even larger clusters. This isn't random. It's a story written by physics itself. Dark matter halos, the invisible scaffolding holding everything together, accumulated and merged over time. Smaller halos fused into larger ones. Gas fell deeper into these gravitational wells, heating up to extreme temperatures. And at the heart of galaxies, supermassive black holes unleashed torrents of energy into their surroundings. All these forces combined, gravity, heat, radiation, to fundamentally transform the nature of galaxies and the groups they inhabited. And now, for the first time, we can watch it happen. Scientists track populations of similar galaxies across different cosmic epochs, find a particular type of galaxy at one distance from us, looking back 1.5 billion years, then find its descendants at another distance, seeing what it became billions of years later. The catalog becomes a time machine, revealing how different types of galaxies emerged and transformed. But there's more. The data reveals something profound about environment. Galaxies living in crowded groups don't evolve the same way as isolated galaxies drifting alone in the void. Group members are constantly brushing past each other, colliding more frequently. The hot plasma between them heats their gas. These environmental factors, the sheer proximity to neighbors, the cosmic friction, accelerate evolution dramatically. Active, star-forming galaxies transform into quiet, quiescent ones, far faster than they ever would in isolation. From chaos to order, from violent creation to peaceful extinction. The groups tell the story of how the universe matured, how the wild cosmos of the early universe gradually settled into the structured, organized cosmos we see today. Imagine you're watching a cosmic transformation unfold across billions of years. In the young universe, galaxies were chaotic and wild. Irregular shapes, brilliant with newborn stars, erupting with energy in every direction. Then something changed. The galaxies grew older. Their star formations slowed to a trickle, and their shapes became orderly and serene. This wasn't random. It was a shift that coincided perfectly with the universe's dark matter reaching a turning point. From rapid growth to slower consolidation. Nearly 1,700 galaxy groups cataloged across the cosmos prove it. They confirm our theories about how the universe builds structure. They validate our models of what kills star formation. They show us how the cosmic web stretches across the largest scales imaginable. But here's what's truly haunting about this cosmic architecture. The universe is mostly empty. Between the glowing threads of the cosmic web stretch voids, regions so vast, so utterly barren, that they dwarf anything in human experience. These aren't small holes. These are continuous volumes of nothingness, extending for hundreds of millions of light years in every direction. The largest known void spans roughly 1 billion light years across. Think about that. Light itself, the fastest thing we know, would take 1 billion years to cross it. 1 billion years. That's longer than the entire history of complex life on Earth. When you venture into a void, structure formation simply fails to occur. Almost no galaxies drift through. Almost no stars ignite. Almost no matter of any kind exists. If you stood at the center and looked in any direction, you'd see darkness stretching for tens of millions of light years before the nearest galaxy appeared. A cosmic desert. An immense prison of emptiness. Here's the strangest part. The voids weren't always this empty. They created themselves. In the early universe, some regions started out just slightly less dense than average. Slightly less dense means slightly less gravity. And when gravity is weaker, matter doesn't stick around. It flows elsewhere. Like water draining downhill, matter streamed out of these regions toward denser areas. And as matter left, the voids became even less dense. Even less dense meant even stronger matter exodus. Gravity tipped the scales. For billions of years, this cascade continued. Voids grew larger. Voids grew emptier. Meanwhile, All that evacuating matter piled up at the boundaries, forming filaments and dense nodes where galaxies cluster together. The result? An increasingly extreme universe? The cosmos didn't distribute matter evenly. Instead, it created vast, empty cathedrals and compressed almost everything into thin threads and dense knots. But these voids aren't useless cosmic wastelands. They're actually perfect laboratories. In crowded regions, galaxies move under competing forces, the universe's expansion tugging them apart, while local gravity yanks them together. It's chaotic. It's messy. It's impossible to untangle. In voids, local effects vanish. Gravity becomes negligible. Galaxies drift like boats on a current, responding purely to cosmic expansion. This makes voids ideal cosmic measuring sticks. By watching how galaxies move in voids, scientists can determine exactly how fast the universe is expanding and how dark energy drives that acceleration. Voids also test whether our models of reality actually work. The number of voids, their sizes, their distribution, all depend sensitively on dark matter's behavior and the initial conditions born from the Big Bang. If we observed more voids than theory predicts, or fewer, it would be a red flag. Something fundamental would be wrong with our understanding. So far, the counts match. The voids appear where we predicted. Their sizes align with our models. The evidence stacks up that we're capturing the broad outlines of cosmic structure correctly. Yet the voids remain unsettling. The universe could have been different. It could have spread matter more evenly, creating a gentler cosmos where structure formed everywhere, where emptiness was impossible. Instead, it chose extremity. Vast oceans of nothing, punctuated by islands of brilliant complexity. In a sense, we don't live in a universe. We live in the thin walls between voids. Imagine standing alone under a night sky utterly unlike ours. Gravity has done its work, pulling matter into threads and filaments, leaving behind vast cosmic voids. The galaxies scattered across your sky would be sparse, fewer, dimmer, and clustered in ways that would make you question what lies beyond. You'd look up and conclude the universe is smaller than it truly is. You'd be looking at an illusion created by geography alone. But there's something else happening in that sky. Light, ancient light, is being stretched. Every photon streaming toward us from the most distant galaxies has been warped by the expansion of space itself. Ultraviolet light becomes visible. Visible light becomes infrared. By the time these photons travel 13 billion years across the cosmos and finally strike our detectors, their wavelengths have expanded 14 to 16 times over. A factor of 15 is not unusual. This transformation has a name: redshift. It's a fingerprint. It's a cosmic clock. And it reveals something profound about the universe's history. Here's the elegance of it. Hydrogen atoms emit light at a precise wavelength, 92 nanometers in the ultraviolet. When astronomers detect that same hydrogen line at 1,380 nanometers in the infrared, they know exactly what happened. The light was stretched by a factor of 15. That number contains a revelation. When that galaxy first emitted its light, the universe was 15 times smaller. Every distance was compressed. Every wavelength was squeezed. Space itself has expanded 15-fold in the time it took those photons to reach us. Now picture what that galaxy actually looked like when it was young. Hot stars blazed with ultraviolet and blue light, the light of stellar youth. We see none of that today, not because the stars have changed, but because the universe has transformed the light en route. Every ultraviolet photon has shifted into the near infrared. Every visible photon has stretched into the mid-infrared. The entire spectrum of that ancient galaxy has vanished beyond what human eyes can perceive. This is why the James Webb Space Telescope exists. Webb was designed for one purpose: to see what Hubble could not. The older telescope, revolutionary as it was, operated mainly in visible and ultraviolet wavelengths. It was blind to the transformed light streaming from the universe's most distant reaches. Webb, though, covers wavelengths from 0.6 microns all the way to 28 microns. Its near-infrared camera stretches from 0.6 to 5 microns. Its mid-infrared instrument extends from 5 to 28 microns. Together, these instruments capture light that has been stretched by factors ranging from 2 to more than 20. Light that simply didn't exist for any previous space telescope to observe. But there's a problem. Stretching a wavelength doesn't just change its color. It spreads the energy across a broader range, making the source appear dimmer. At the same time, the expansion of space itself slows the rate at which photons arrive at our detectors. These two effects combine catastrophically. Distant, high redshift galaxies are not just faint. They're impossibly faint, even though they're intrinsically luminous. Webb had to overcome this through sheer technological supremacy. Its mirror is larger than anything ever launched into space, collecting more light than any previous telescope. Its instruments are engineered to detect signals so faint they'd be drowned out by ordinary noise. And critically, it orbits 1 million miles from Earth at the second Lagrange point, where our planet's heat and light cannot interfere. This isolation allows Webb to capture photons that have been traveling through the void for 13 billion years. Light so ancient it carries the universe's own autobiography. The observations confirm it. Light from the most distant galaxies is indeed stretched by the predicted amounts. The redshift measurements match the theory. The expansion of space is real. But here's where the story takes a turn. As Webb has peered deeper and deeper, it has revealed something that doesn't fit the models we built. The universe is expanding. That's confirmed. But how it's expanding and why contains a mystery we're only beginning to confront. Imagine you're trying to measure how fast a train is moving, but every time you check, you get a different answer. One method says it's going 67 miles per hour. Another says 73. The difference seems tiny, just 6 miles per hour. But here's the problem. Both measurements are solid. Both have been triple-checked. Both use completely different equipment. So which one is right? This isn't about trains. It's about the entire universe. And the discrepancy is so real, so persistent, that it has a name: the Hubble tension. And it might be pointing us towards something revolutionary. Here's where it starts. The universe is expanding. We know this. But when scientists try to measure exactly how fast, they run into trouble. They're getting two fundamentally different answers, and they can't figure out why. The first measurement looks backward in time. Astronomers peer at the cosmic microwave background, the ancient light left over from the Big Bang itself, the oldest light in existence. This radiation carries a map of the universe from 13.8 billion years ago, written in patterns of hot and cold spots. Those patterns tell us everything about the universe's properties back then. And when scientists use that information to calculate how fast the universe should be expanding today, they get 67 kilometers per second per megaparsec. The second measurement looks at what's nearby. Astronomers point telescopes at distant galaxies and use something called standard candles, Cepheid variable stars, and type Ia supernovae. These objects have a known intrinsic brightness. By comparing how bright they appear to Earth versus how bright they actually are, astronomers calculate their distance with precision. Combine that with measurements of how fast these galaxies are moving away from us, and you get an expansion rate of 73 kilometers per second per megaparsec. 6 kilometers per second doesn't sound like much, but in the language of statistics, it's a screaming alarm. This gap has been verified again and again. Data from multiple satellites, ground-based telescopes, Hubble Space Telescope observations spanning decades, and now the James Webb Space Telescope, the most powerful observatory humanity has ever built, has confirmed it using 3 independent methods. All 3 agreed with each other. All 3 matched Hubble's results. The tension isn't going away, it's getting louder. Here's why this matters. The early universe and the late universe are disagreeing about a fundamental property of reality. One is telling us the universe expands at one rate. The other is telling us it expands at another. Both can't be right if our understanding of cosmic evolution is correct. So what's going on? Maybe dark energy, the mysterious force driving cosmic acceleration, isn't what we think it is. We've assumed it stays constant over time. But what if it's changing? What if dark energy was stronger in the early universe and has weakened as billions of years passed? That would explain why the expansion rate differs between then and now. Or maybe there's unknown physics we haven't discovered yet. Perhaps something in space, dark matter, hidden fields, forces we've never encountered, is subtly bending light or altering how measurements work. Perhaps interactions between light and dark matter are biasing our calculations in ways we don't yet understand. Perhaps we're making a mistake. Some hidden, systematic error in one or both methods that's eluded detection despite countless checks. But there's one possibility that's even more tantalizing. What if the tension is real? What if it's not a measurement problem or a misunderstanding? What if the universe actually evolved in ways our current theories don't explain? What if genuinely new physics exists? Unknown forces, undiscovered particles, physics beyond what we've written in our textbooks. If that's true, everything changes. The mystery of the Hubble tension isn't just about a number. It's about understanding how the universe was born, how it evolved, and where it's heading. Get this wrong, and you misunderstand the cosmos at the most fundamental level. You miscalculate the universe's true age. You misjudge its ultimate fate. You miss something profound about reality itself. And speaking of profound cosmic mysteries, scientists have now confirmed something that had only lived in theory for decades. Dark matter. It comprises 85% of all matter in the universe. It doesn't glow. It doesn't shine. It doesn't interact with light in any way we can detect. It's invisible, elusive, and everywhere. A ghost that holds galaxies together through gravity alone. Its nature's still one of science's greatest unsolved puzzles. Everything we see in the universe, every star, every galaxy, every planet is floating on an invisible ocean. We know it's there only because we can feel its pull. Galaxies spin too fast to hold together. Galaxy clusters move in ways that defy what we can actually see. The entire cosmic web, this vast network of galaxies stretching across billions of light years, simply wouldn't exist without it. For decades, physicists built mathematical models. They ran supercomputer simulations. And every time, the answer was the same. Dark matter should be everywhere. Not just clumped at intersections. Not just concentrated in the main highways. Dark matter should thread through the smallest filaments of the cosmic web, connecting galaxy to galaxy like invisible strands, holding the universe together. But here's the problem. Nobody had ever actually seen it there. Until now. Researchers from Yonsei University in Seoul pointed the Subaru telescope, an 8-meter mirror nestled in Hawaii, at the Coma Cluster. This isn't just any collection of galaxies. Over 1,000 of them are packed into this region, 321 million light-years away. It's a cosmic traffic jam, a place where multiple filaments of the cosmic web converge and tangle. The team didn't look for dark matter directly. You can't. Dark matter is invisible. Instead, they used a trick that Einstein himself predicted: gravitational lensing. Imagine light traveling across the universe like a river. Now, imagine a massive, invisible weight sitting in its path. The light doesn't pass straight through. It bends. Space itself warps around that dark matter, and the light curves along with it. From our perspective here on Earth, background galaxies appear stretched, distorted, warped like reflections in a funhouse mirror. By measuring these subtle distortions, and I mean subtle, astronomers can map where the invisible mass actually is. Previous observations had found dark matter in the main filaments of the cosmic web. They detected it at the nodes, those dense junction points where multiple filaments meet. Scientists expected to find it there. It made sense. But this team looked further. They searched the terminal segments, those hair-thin threads that branch off from the main filaments to connect with individual galaxies. The smallest, most delicate strands of the cosmic web. And they found it. Dark matter was there, threading through those tiny filaments, creating a continuous structure that reaches all the way from the densest nodes down to individual galaxies. This wasn't a prediction anymore. This was direct observational evidence. The invisible skeleton of the universe had finally revealed itself. Think about what this means. Galaxies aren't drifting randomly through empty space. They're not bobbing aimlessly through a void. They're sliding along dark matter highways, superhighways carved through space itself by the gravitational influence of invisible matter. These highways guide galaxies toward clusters, toward denser regions, toward each other. The Coma Cluster sits on something called the Great Wall. When astronomers first discovered the Great Wall, it shattered their understanding of cosmic structure. A sheet of galaxies stretching across hundreds of millions of light-years. A wall of matter spanning distances so vast that light takes millions of years to traverse it. The Coma Cluster is one of the densest regions on that wall, a convergence point where multiple dark matter filaments come together like threads braiding into rope. Now, you might think, if dark matter is everywhere, why wasn't this discovered earlier? The answer lies in the extraordinary difficulty of these measurements. The distortions caused by dark matter are tiny. Background galaxies appear only slightly stretched. To detect this signal, you need to measure the shapes of hundreds of galaxies with incredible precision. You need to find patterns in how they're warped. You need to remove every other source of distortion: atmospheric turbulence, telescope imperfections, instrumental noise, and still pull out the gravitational fingerprint of dark matter. The Subaru telescope's 8.2-meter mirror and its advanced instruments made this possible. The team analyzed hundreds of background galaxies, searching for systematic patterns in their shapes, and there it was. The gravitational influence of dark matter, threading through space, bending light, warping images, leaving an invisible signature that finally became visible. This matters because it confirms what theory predicted, but observation had never proven. Dark matter doesn't just concentrate in nodes. It genuinely pervades the entire network. The cosmic web is more than just a skeletal frame. It's a complete structure, woven together from the smallest threads to the largest sheets. But there's another discovery happening right now that's forcing us to completely reimagine the scale of this invisible universe. For years, astronomers had a number they trusted: 200 billion galaxies. This came from Hubble surveys. tiny patches of sky meticulously studied and counted, then extrapolated across the entire observable universe. The math checked out. Multiple independent surveys agreed. It seemed solid. Then the James Webb Space Telescope looked at the same regions. Webb's deep fields showed significantly more galaxies than Hubble had detected. Galaxies packed more densely into space. Galaxies smaller and fainter, and more numerous than anyone anticipated. The 200 billion figure, the one that had stood unchallenged for years, suddenly looked too low. The universe is more crowded than we thought. There are more galaxies, more dark matter, more structure, more complexity woven into the cosmic web. And now, for the first time, we're actually seeing the invisible architecture that holds it all together. The universe's largest structures have revealed their hidden skeletons. And that skeleton might be far more populated, far more intricate, far more vast than anyone ever imagined. Imagine standing on a beach at sunset. Pick up a single grain of sand. Now picture 100 planets orbiting distant stars somewhere in the cosmos right now. For every grain beneath your feet. That's not poetic exaggeration. That's where the numbers are taking us. For decades, astronomers thought they had a handle on the universe. Hundreds of billions of galaxies. That number felt vast enough. But then the James Webb Space Telescope turned its gaze to the deepest patches of sky and changed everything. The observations caught scientists off guard. Where Hubble saw empty space or faint smudges, Webb revealed entire populations of galaxies hiding in plain sight. Some lurked behind cosmic dust that blocks visible light but lets infrared slip through like goats passing through walls. Others were simply too faint for older telescopes to detect. The result? A single deep field observation suggested the universe might contain not hundreds of billions of galaxies, but trillions. If that's true, and here's where your mind should start spinning, then everything we calculated about the cosmos needs to be rewritten. Tenfold. Maybe more. Start with our own galaxy. The Milky Way hosts roughly 200 billion stars. Assume each one has, on average, just a single planet orbiting it. That gives us 200 billion planets just here, in our cosmic neighborhood. Now multiply by the old estimate, 200 billion galaxies. You get 400 quintillion planets, 4 followed by 21 zeros. But if the universe truly harbors trillions of galaxies instead, that number doesn't just grow, it explodes. We're talking 4 quadrillion quintillion planets, possibly more. The scale collapses our intuition. Our brains evolved to understand handfuls and herds, not infinities. Yet scientists tread carefully. Webb observed relatively small patches of sky in obsessive detail. Perhaps those patches aren't representative. Perhaps they happen to fall in cosmic neighborhoods, denser than average. Perhaps galaxy distribution varies wildly across the universe. Thick here, sparse there, like an uneven forest. So researchers are running new surveys. They're scanning larger portions of the sky with slightly less depth, hunting for patterns. Early results are telling a consistent story. Multiple deep field observations in different directions keep revealing the same high densities. This isn't random noise or cosmic coincidence. The signal is real. If confirmed, the implications become almost too enormous to contemplate. Trillions of galaxies, each containing billions, sometimes trillions of stars, each star potentially surrounded by planets. The probability of Earth being the only place where life ever sparked? Statistically, it approaches zero. Life should be common, maybe even inevitable. But here's where the true strangeness begins. Even in these distant galaxies, billions of light years away, seen as they were in the universe's youth, something bizarre is unfolding. These galaxies are manufacturing stars at a frantic pace, 10 times, 100 times faster than galaxies like ours do today. That shouldn't be possible. Star formation has a speed limit, governed by the laws of thermodynamics itself. Before gravity can collapse gas into stars, that gas must cool. Hot gas pushes outward with pressure, resisting the inward crush of gravity. Only when gas cools sufficiently does gravity finally triumph, allowing clouds to fragment and ignite stellar nurseries. This cooling takes time. It always has. In our modern universe, a typical molecular cloud might birth just a few stellar masses of new stars annually. Most of the gas gets blown away by stellar winds or superheated by radiation. The process is inefficient by necessity. Physics allows no shortcuts. Yet the early universe operated by different rules. Galaxies only a few 100 million years old, mere infants compared to our 13.8 billion-year-old cosmos, display stellar populations that could only have formed if they were somehow circumventing the laws of thermodynamics, somehow cooking stars at rates that seem physically impossible. The universe is showing us it's far vaster than we imagined, but it's also revealing that in its earliest moments, it played by rules we're only beginning to understand. And perhaps that's the most humbling discovery of all. Picture this. The early universe is a cosmic furnace operating at full throttle. Galaxies aren't just making stars. They're manufacturing them with a ferocity that shouldn't be possible. Here's the mystery. When astronomers measure how bright these ancient galaxies shine and compare that to how much mass they contain, the numbers don't add up. These early galaxies are converting gas into stars far faster than our current theories allow. They're doing the impossible. So how do we even know this is happening? It comes down to light. A galaxy's brightness tells us how many stars live inside it and how intensely those stars burn. Young, massive stars. They're cosmic infernos, blazing with an intensity that makes our sun look like a candle. By analyzing the rainbow of light streaming from a distant galaxy, its spectrum, scientists can measure how rapidly new stars are being born. Then they do the math. They compare that birth rate to the galaxy's total mass, and that's when the problem becomes undeniable. These ancient galaxies are converting their available material into stars at rates that shouldn't work. Why? That's where things get interesting. One clue lies in the universe's architecture. Early on, space was cramped. Galaxies weren't spread out like islands in an endless ocean. They were packed closer together, squeezed into smaller volumes. Gravity was working overtime. When matter compresses into tighter spaces, clouds collide more often. And collisions? They trigger star formation. More collisions meant more stars igniting into existence. Simple, brutal efficiency. But there's more to the story. The composition of the gas itself might matter. The very first stars formed from pure hydrogen and helium, pristine material forged in the Big Bang. Modern stars, by contrast, form from recycled gas, enriched with heavy elements left behind by previous stellar generations. These heavy elements help gas cool down more effectively through various atomic processes. Here's the paradox. You'd think that would speed things up, but it might actually slow things down. Pure hydrogen, stripped of these heavy elements, could collapse more rapidly under the right conditions. Fewer cooling channels means fewer complications, simpler collapse, faster star birth. The early universe's environment was also radically different. Galaxies collided constantly. When two galaxies merge, something dramatic happens. Their gas gets funneled toward the center, piling up into dense, compact regions. And in those densely packed cores, something extraordinary occurs: starbursts. Briefly, just for millions of years, these regions explode into frantic star production, thousands of star masses worth of new stars, born in intense bursts of creation. Yet even with all these possibilities, scientists are still puzzled. Because here's the real problem. If ancient galaxies were truly burning through their gas reserves at these insane rates, they should have run out of fuel almost instantly. Imagine a galaxy converting gas into stars 100 times faster than galaxies do today. By the math, it should exhaust its supply in just 1/100th of the normal time. It should be empty, but it wasn't. Many early galaxies show vast populations of stars that required sustained star formation over millions, even tens of millions of years. Where was all that gas coming from? The answer might be cosmic plumbing. Computer simulations reveal something stunning. Gas can flow directly from intergalactic space into galaxies. These aren't random flows. They follow the cosmic web itself, channeling cold gas along vast filaments of matter that crisscross the universe. An endless supply. A cosmic pipeline feeding the star factories without requiring massive initial reservoirs. Just a steady stream, continuously replenishing what gets burned away. What emerges from all this is a sobering realization. The early universe wasn't just a younger version of our cosmos. It was fundamentally different. Different physics, different conditions, different outcomes. And that difference becomes even more apparent when you zoom out to see the universe's largest structures. The grandest things gravity can build are galaxy clusters. Cosmic cities containing hundreds or thousands of galaxies, crammed into spaces just a few million light years across. These clusters are the nodes where the cosmic web's massive filaments intersect. Imagine the densest city on Earth. Then multiply that density by trillions. Now scale it to intergalactic proportions. A single massive cluster weighs roughly 100,000 billion times more than our sun. One followed by 14 zeros. Let that sink in. And here's the shocking part. Most of that mass isn't even in the galaxies themselves. It's spread through the space between them. Hot plasma and invisible dark matter, creating a gravitational scaffolding that holds everything together. Take the Coma Cluster. Over 1,000 galaxies orbit within it. The entire structure weighs about 10,000 trillion solar masses. Light itself takes millions of years just to cross from one edge to the other. If you could somehow stand in the middle of this cluster, you'd be surrounded. Galaxies in every direction, spirals, ellipticals, a sky absolutely packed with distant light, and it's not silent. These clusters roar with energy. Intense X-rays flood the space between galaxies. Why? Because the space between isn't empty. It's filled with superheated plasma, gas hotter than tens of millions of degrees. That heat comes from the same gravity that assembled these structures in the first place. Gravity doesn't just build, it burns. It creates conditions so extreme that the void between galaxies becomes an invisible furnace. The universe at these scales is almost incomprehensible, but that's exactly why we need to comprehend it, because understanding how galaxies form, how they feed, and how they cluster together tells us something profound about our own place in this cosmos. We're not accidents in an empty universe. We're part of a system of staggering complexity and violence and beauty, all held together by the same force that drops an apple from a tree. Imagine galaxies like water rushing down a drain. As they plummet into a galaxy cluster's gravitational well, friction ignites them. The gas heats to millions of degrees. It blazes across the electromagnetic spectrum. Visible light, X-rays, ultraviolet radiation, all screaming outward. This is the violent birth cry of the universe's largest structures. But here's where things get strange. These clusters act like cosmic magnifying glasses. Their gravity is so immense they actually bend space itself. Light from galaxies, billions of light years behind them, curves around the cluster, like water flowing around a boulder. And when light bends like this, something remarkable happens. You see the same distant galaxy multiple times, stretched into ghostly arcs and rings, like a funhouse mirror, reflecting the cosmos itself. Astronomers realized they could use this cosmic distortion to weigh these clusters, and when they did the math, they found something troubling. The math didn't add up. The visible galaxies in a cluster, all those brilliant points of light, account for just a few percent of the cluster's total mass. The superheated plasma swirling between them makes up another 10 to 15%, but that leaves 85% completely unaccounted for. It's invisible. It emits no light. It reveals itself only through gravity, a ghostly pull that keeps everything bound together. This invisible substance is dark matter, and it poses one of science's most profound questions. What is it? We know dark matter must exist, because without it, these clusters would tear themselves apart. The visible galaxies move far too quickly for the gravity of ordinary matter alone to hold them. They should be flying apart in all directions. Instead, they stay together. Dark matter provides the gravitational glue. Galaxy clusters represent the largest structures that will ever remain intact. Beyond them lie superclusters, collections of multiple clusters connected by gossamer filaments of galaxies. These superclusters are impressive, yes, but they share a crucial weakness. They're not gravitationally bound. They're merely regions where clusters happen to be relatively close together, and cosmic expansion will eventually rip them apart. But clusters have a different fate. As the universe ages, they'll swallow more galaxies from the surrounding cosmic web. They'll grow more massive. Their gravity will strengthen. Billions of years from now, the galaxies within clusters will collide and merge. Distinct galaxies will vanish. In their place will arise single, colossal elliptical galaxies, cities of hundreds of billions of stars all orbiting one center. Yet even this stunning prediction faces a cosmic complication. Clusters aren't simply being pulled together by gravity. They're being pushed apart by something far more mysterious, something far more powerful. That something comprises 68% of all existence. It's not dark matter. It's not ordinary atoms and molecules. It's not radiation. It's dark energy. We don't know what it is, but we know what it does. It pushes space apart. It accelerates cosmic expansion. And its discovery rewrote everything we thought we understood about the universe's fate. In 1998, astronomers made an observation that shattered decades of assumptions. They were studying Type 1, a supernovae, exploding white dwarf stars that detonate with remarkably consistent brightness, making them perfect cosmic distance markers. Using these supernovae, they could measure how fast the universe was expanding at different times in its history. The expectation was straightforward. Gravity should be slowing expansion down. After all, every particle in the universe pulls on every other particle. Over billions of years, this gravitational tug should gradually break the expansion. Eventually, gravity might even reverse it, pulling the universe back into collapse. Instead, the data revealed the opposite. Expansion wasn't slowing, it was accelerating. Distant supernovae were farther away than they should be. Something was pushing space apart faster and faster. Dark energy. But dark energy violates everything we thought we knew about how things work. Consider ordinary matter. As the universe expands, it gets diluted. If you have 1 particle per cubic meter, and space doubles in volume, suddenly you have 1 particle per 2 cubic meters. The density decreases. Dark energy doesn't follow this rule. As the universe expands, dark energy's density stays the same. The universe grows larger, and dark energy's total amount increases, while its concentration remains constant. More universe means more dark energy, always. This has a staggering consequence. Early on, when the universe was dense and tightly packed, matter and radiation dominated. Gravity was the architect of cosmic structure. Galaxies formed, clusters coalesced. Everything was shaped by gravitational collapse, but as the universe expanded, matter spread out and diluted. Its influence weakened. Meanwhile, dark energy's influence grew. About 5 billion years ago, a cosmic crossroads arrived. Dark energy overtook gravity as the dominant force in the universe. And from that moment onward, the universe's fate was sealed. Expansion would never reverse. It would accelerate forever. Gravity became secondary. Dark energy became the maestro conducting the cosmic symphony. Right now, this acceleration shapes everything we observe. The observable universe spans 93 billion light-years across. Not because it's 93 billion years old, but because dark energy has been pushing space outward for billions of years. Without dark energy's relentless push, the universe would be smaller. Expansion would have proceeded at a slower pace. The most distant galaxies we can see would be much closer. Dark energy transformed the universe from a place where gravity shapes all destiny into a place where an invisible force pulls all structure apart. We've discovered what dominates the cosmos. We've measured its effects with precision, but the deepest question remains unanswered. What is dark energy? And that mystery, that profound unknown, defines the frontier of modern physics. Imagine standing at the edge of everything you can see. Beyond that edge lies the rest of the universe. Trillions upon trillions of galaxies stretching into the darkness. But here's the thing, you will never see them. They're racing away from you so fast that their light will never catch up, and as they disappear, something even stranger happens. Time itself begins to break down. This is the consequence of dark energy, a force that makes up 68% of everything that exists, yet remains almost completely mysterious. Dark energy is pushing space apart. And if it stays as strong as it is now, cosmic expansion will accelerate forever. Galaxy clusters will hold together through gravity. But everything beyond our local group, the Milky Way and its nearby galactic neighbors, will eventually slip beyond what we call the cosmic horizon. Trillions of years from now, any observer in our galaxy will look out into the void and see nothing, only darkness. The rest of the universe will have raced away so fast that light itself cannot bridge the gap. But that's just the mild version of the future. There's a darker possibility. What if dark energy doesn't stay constant? What if it actually gets stronger over time? Then we face something called the Big Rip. Cosmic acceleration becomes acceleration upon acceleration. Dark energy grows so powerful that it overwhelms gravity on smaller and smaller scales. First, it would tear apart galaxy clusters, then galaxies themselves, then star systems, then planets, then molecules, then atoms. The universe doesn't fade away quietly. It gets ripped apart from the inside out. This isn't confirmed. It's theoretical. But scientists are taking it seriously enough to measure dark energy's properties, trying to figure out if it's possible. And right now, the measurements suggest dark energy has held relatively steady for the past several billion years. Its strength appears captured by something physicists call the equation of state parameter, a number that measures how dark energy's pressure relates to its density. That number looks to be approximately -1, which is exactly what Einstein proposed over a century ago, a cosmological constant. The universe's gravity alone would crush everything into oblivion, so Einstein added a repulsive force to keep it in balance. He called it the cosmological constant. He was right. Except the universe isn't in balance, it's accelerating. But here's where it gets really strange. When space expands, time doesn't behave the way we think it should. Take a galaxy at the very edge of what we can observe from where we stand. That galaxy is racing away from us at nearly the speed of light. Not because it's moving through space, but because space itself is expanding. Now, Einstein's theory of relativity tells us that time behaves differently for objects moving at extreme speeds. The faster something moves relative to you, the slower its clock ticks from your perspective. So from our viewpoint, time in that distant galaxy is crawling. Clocks there tick in slow motion. We see that galaxy frozen, locked in a particular moment of its evolution. And this is where relativity gets beautifully strange. If you were an observer in that distant galaxy, something completely different would be true. Your clocks would tick normally. You would see our galaxy racing away from you at near light speeds. From your perspective, our clocks would be the ones running slow. Both of us would be right. Time dilation isn't absolute, it's relative, and that creates something profound at the cosmic horizon. As galaxies slip beyond that boundary and their light can no longer reach us, we see them freeze at the exact moment they cross over. From our frame of reference, their time has stopped completely. They're locked in place, unreachable, and unchanging. Meanwhile, galaxies closer to us experience far less time dilation. Nearby galaxies recede slowly enough that the effect is barely noticeable. And galaxies in our local group? They're not receding at all. Gravity holds them together. Time passes normally for them relative to us. So imagine the observable universe from our vantage point. It's filled with objects at completely different rates of time progression. Distant galaxies moving in near slow motion. Nearby galaxies moving at normal speed. Us, caught somewhere in between. Watching the cosmos age at different rates depending on how far away things are. The universe isn't just expanding. It's creating its own hierarchy of time. And we're only beginning to understand what that means. Imagine you're standing at the edge of a vast library, looking down an impossibly long corridor lined with books. The books closest to you are crystal clear. You can read their spines, see their details, but as your eyes travel deeper into the corridor, the books become hazier, dimmer, more difficult to distinguish. And then, far down the hall, they disappear entirely into darkness. This is what astronomers have been looking at for decades. When we peer out at distant galaxies, we're not just looking across space. We're looking backward through time. The farthest galaxies we observe appear frozen in the early universe, exactly as they were billions of years ago. But here's the catch. Time isn't the same everywhere. Einstein showed us something radical. Time doesn't flow at one universal pace. Intermediate distance galaxies show moderate time dilation. Nearby galaxies experience time at rates similar to ours. What you're actually witnessing is a temporal gradient stretching across the entire cosmic horizon. And gravity makes it even stranger. Regions of stronger gravity experience slower time relative to weaker gravity zones. Near a massive galaxy cluster, time passes slightly slower than in the voids between filaments. Near a black hole, time slows dramatically. Right at the event horizon, time appears to stop completely from our perspective. Every point in space has its own unique experience of time's passage. For us, these differences are negligible. Our lifespans are too short to notice. Even over Earth's entire history, the effects are barely measurable. But when you're observing across billions of light years and billions of years of cosmic history, time dilation becomes impossible to ignore. Here's the real puzzle. When the James Webb Space Telescope observes those distant galaxies, it's seeing them as they appeared billions of years ago. But from those galaxies' perspectives, time kept flowing normally. They've evolved. They've changed. They've possibly merged with other galaxies or collided and died. We'll never see those later stages. The light showing us what happened next is still traveling through space, stretched and diluted by cosmic expansion. What we see is a universe frozen in layers of the past, each layer a different cosmic epoch, a different moment in time. For over 3 decades, the Hubble Space Telescope did the impossible. Launched in 1990, Hubble revolutionized astronomy. Its ultra-deep field image showed nearly 10,000 galaxies in a patch of sky the size of a grain of sand held at arm's length. Scientists called it the deepest view of the universe ever obtained. Then Webb looked at the exact same regions. Where Hubble saw empty darkness, Webb detected countless additional objects. Faint red smudges, invisible to Hubble, blazed clearly in Webb's infrared detectors. The darkness wasn't empty at all. It was filled with galaxies that Hubble simply couldn't see. The difference comes down to something fundamental: wavelength. Hubble operates primarily in visible and ultraviolet light, with some near-infrared capability. Its instruments are optimized for the wavelengths human eyes can detect, perfect for nearby galaxies. But for the most distant galaxies, something extraordinary happens. The light they emit has been traveling toward us for billions of years, and the universe itself has been expanding the entire time. That expansion stretches the light waves themselves. What left those ancient galaxies as blue and ultraviolet light arrives at our telescopes as infrared radiation. Hubble's visible light detectors couldn't capture it. The galaxies remained invisible, hidden not by dust or distance, but by the fundamental properties of cosmic expansion itself. Webb was designed specifically to solve this problem. Its instruments cover infrared wavelengths from 0.6 microns all the way to 28 microns. This range captures light from galaxies at virtually any redshift. To achieve this sensitivity, the telescope operates at temperatures near absolute zero, cold enough to prevent its own heat from overwhelming the faint infrared signals it's trying to detect. The results are staggering. Regions Hubble imaged as black voids now show structure. Galaxies appear where nothing seemed to exist. The cosmic landscape has gained depth and detail that was literally invisible before. Cosmic dust adds another layer to this story. Dust particles scatter and absorb visible light, but they allow infrared to pass through relatively unimpeded. Star-forming regions are often shrouded in thick dust clouds. Hubble saw these regions as dark patches, empty voids in the cosmic tapestry, but they weren't empty. They were birthplaces. Stellar nurseries, hidden from visible light but revealed in infrared. Webb could see through the dust and witness galaxies being born, stars igniting in clouds of gas and dust that Hubble could never penetrate. We spent decades believing we were looking at the deepest universe. We were wrong. The universe was simply waiting for us to learn how to see. For centuries, we thought we knew what the universe looked like. The Hubble Space Telescope showed us deep space in all its glory. Vast, mysterious, scattered with distant galaxies like islands in an infinite ocean. It was our most powerful eye on the cosmos. And then, in 2022, something extraordinary happened. The James Webb Space Telescope turned its gaze toward the same patches of sky Hubble had already studied. And what it saw was staggering. Where Hubble showed sparse galaxies against a black void, Webb revealed hundreds of faint galaxies filling every gap. The universe suddenly looked crowded, alive, impossibly dense with activity. But here's the catch. Webb wasn't seeing something new. It was seeing what was always there. The secret lies in a simple truth about light. Human eyes evolved to see visible light. The thin slice of the electromagnetic spectrum our biology happens to detect. Hubble followed this same constraint, looking at the universe through visible light. It saw what we would see if we could float in space and look around. That's not a weakness. It's exactly what made Hubble revolutionary. It discovered dark energy. It measured how fast the universe is expanding. It found supermassive black holes lurking at the hearts of galaxies. Hubble transformed our understanding of the cosmos itself. But Webb sees something our eyes never can. It detects infrared radiation, heat signatures invisible to human vision, but absolutely critical for understanding how the universe actually works. And when Webb pointed its infrared eyes at distant galaxies, something profound became clear. Our visible light view of the universe is fundamentally incomplete. We've been looking at only half the picture. Galaxies choked in cosmic dust, they appeared as dim, faint smudges to Hubble, if they showed up at all. But to Webb, they blaze like beacons. Stellar nurseries, the regions where stars are actually being born, were hidden behind veils of dust that visible light cannot penetrate. Webb sees straight through, revealing star formation in environments that were previously opaque to us. Scientists can now measure how much dust fills different galaxies across cosmic time. They can trace how dust shapes the evolution of entire galaxies. They can study the universe in eras where visible light tells only a partial story. This wasn't just a technical upgrade. This was seeing the universe with new senses altogether. And what Webb revealed shattered something fundamental: our timeline of cosmic history. When astronomers construct models of the early universe, they have one crucial constraint: time. In the beginning, there was the Big Bang. Space expanded. It cooled. About 380,000 years later, an eye blink in cosmic terms, atoms formed. Electrons captured by nuclei. Light broke free, flooding the universe for the first time. Hundreds of millions of years passed in darkness, and then, gradually, the first stars ignited. These stars gathered. More stars formed. These stars clustered into the first galaxies. But the process should have been slow, deliberate. The universe simply hadn't existed long enough to build anything elaborate. In the first 500 million years, galaxies should have been rare, small, dim, and simple. Structures containing just a few billion stars at most. Physics seemed clear. Time was the limiting factor. Then Webb looked. And what it found contradicts everything. Within the first 400 million years after the Big Bang, when the universe was barely old enough for elementary structures to exist, it was already blazing with light. Massive galaxies, enormous structures, blazing across space like nothing theorists predicted. Webb observed it. Independent surveys confirmed it. Different instruments verified it. The observations all pointed to the same impossible conclusion. The early universe was far more luminous than any model predicted. Scientists now call it the too much light, too early problem. And the numbers make it impossible to ignore. Researchers calculated the total amount of light produced by all galaxies in the first billion years after the Big Bang. They compared this prediction, based on our best theories of how structure forms in the universe, to what Webb actually observed. The observations exceeded predictions by factors of 2 to 10. 2 to 10 times more light than models said should exist. This isn't a small disagreement. This isn't the kind of mismatch you can smooth over with minor adjustments. This is a fundamental challenge to how we understand galaxy formation itself. Something about the early universe allowed it to produce stars and galaxies with staggering efficiency, far more efficient than the processes working today. We don't know what that something is. Several possibilities have emerged. Perhaps the initial mass function was different back then. This function describes what mix of stellar sizes forms when stars are born. Today, star formation produces mostly small stars, with only a few truly massive ones sprinkled in. But maybe the early universe worked differently. Maybe it produced proportionally more massive luminous stars. Massive stars burn brighter. They die faster. They produce more light in a shorter time. If the early universe manufactured stars this way, the excess light problem might make sense. But that's just one possibility, and it opens new questions. Why would star formation work so differently then? What changed? What stopped the early universe from continuing to churn out massive stars with such efficiency? We are now facing a mystery as profound as any in modern astronomy. The universe is telling us something we don't yet understand. And for the first time, thanks to Webb's infrared vision, we can finally read what it's saying. Imagine you're looking at the early universe, just a few 100 million years old, and something is deeply, profoundly wrong. The numbers don't add up. The galaxies are too bright. The stars are too abundant. The light pouring out of that infant cosmos is orders of magnitude more intense than our best theories predicted. And with every new observation, the problem gets worse. Here's why this matters. We thought we understood how the universe works. We built elegant mathematical models. We tested them against decades of observations. They worked. But then something unexpected happened. The James Webb Space Telescope started peering deeper into the cosmic past than any instrument before it. And it found galaxies blazing at 600 million years after the Big Bang. Then 500 million. Then 400. Then 300. Each discovery pushed the boundary earlier, revealing a universe far more active and luminous than anyone had imagined. So what's going on? There are several possibilities, and each one reveals something profound about how galaxies actually form. The first is simple. Maybe massive stars dominate the early universe far more than we thought. Massive stars burn with ferocious intensity. Their light output dwarfs that of smaller stars. If the early universe contained more of these cosmic furnaces, the total light production would skyrocket. But here's the catch. We have no good explanation for why the early universe would preferentially create massive stars. Then there's star formation efficiency. In the universe today, it's remarkably wasteful. Most available gas never becomes stars. Instead, it gets superheated by stellar winds and black hole jets. It gets blown away in explosive outflows. It lingers in diffuse clouds, just drifting through space. But what if the early universe was different? What if environmental conditions were just right? Gravity pulling harder, matter denser, everything more conducive to collapse, allowing gas to convert into stars far more efficiently than today. More stars per unit of gas means more light, much more light. Then there's the wild card. Black holes. Supermassive black holes at the centers of galaxies can do something truly spectacular. When they actively consume matter, they don't just shine. They can outshine entire galaxies. We call these active galactic nuclei. And in the early universe, telescopes are finding them everywhere. Galaxies, from just a few 100 million years after the Big Bang, are hosting supermassive black holes that shouldn't exist yet. These objects are eating matter, releasing energy in a fury of radiation and jets, adding their own brilliant light to an already impossible picture. What makes this crisis so frustrating for cosmologists is that the problem doesn't go away, it compounds. Each new observation, each deeper look into the past, reveals more light, more structure, more activity than the standard model allows. The model isn't completely broken. It still nails the cosmic microwave background radiation, element distributions, and the large-scale structure of galaxies. But clearly, it's missing something fundamental about how galaxies form and evolve in those crucial first moments. Solving this might require us to rethink the basics. Maybe dark matter doesn't behave as we assumed. Maybe star formation works through mechanisms we haven't discovered yet. Maybe the Big Bang left the universe in a more complex state than we currently imagine. What remains certain is this: the universe's infancy was far more violent and luminous than anyone predicted. Now, here's where it gets truly humbling. The light we're seeing from that era has been traveling across space for nearly 14 billion years. But that journey tells an even stranger story, because the universe itself has been expanding the entire time. When light left those ancient galaxies, they were relatively close to us. But as that light traveled toward Earth, space itself kept stretching. Galaxies kept receding. By the time that ancient light finally reached our telescopes, the galaxies that created it had moved nearly 47 billion light years away. That's the edge of what we call the observable universe. A sphere with a radius of 46.5 billion light years centered on us. Everything within that sphere, in principle, we could see. We have access to that information. But everything beyond, everything past that cosmic horizon, it's invisible to us. And this is where the truly mind-bending part kicks in. The observable universe isn't the edge of reality. It's just the limit of what we can detect. Space doesn't end at 46.5 billion light years. It keeps going. Galaxies exist out there, just beyond our reach. Stars shine. Planets orbit. Black holes devour matter. Entire universes of activity, proceeds completely unknown to us, completely unobservable from Earth. We know this because the universe looks fundamentally the same no matter where we point our telescopes. The cosmic microwave background, the afterglow of the Big Bang itself, has nearly identical properties across the entire sky. Galaxies distribute themselves uniformly in all directions. There's no edge, no wall, no boundary. It's uniform in every direction we look. That uniformity is the smoking gun. It tells us space extends far beyond what we can see. Picture it this way: the observable universe is a sphere. We live somewhere in that sphere. The edge is 46.5 billion light years away in every direction. But the actual universe? It's far larger, infinitely larger. Somewhere 47 billion light years away, galaxies exist that we will never see. Their light is traveling toward us, slowly, inexorably. But it's not fast enough. That's because space itself is expanding. And it's accelerating. Imagine someone running on a treadmill, sprinting directly toward you. You'd expect them to reach you eventually, right? But what if the treadmill keeps speeding up? What if it accelerates faster than they can run? Then they're doomed. They'll run forward forever, burning energy, making no progress. Because the ground beneath their feet keeps moving away faster than their legs can carry them. That's the fate of light from the most distant galaxies. Space is the treadmill. Cosmic expansion is the acceleration. And no matter how far that light travels, it will never reach us. The universe is vast beyond comprehension, but our view of it is infinitely more limited than that. Imagine standing on a platform while the ground beneath your feet accelerates away. That's happening right now. The universe is expanding, and it's speeding up. Here's the brutal reality. There are regions of space so far away that light from them will never reach us. Not in a million years. Not in a trillion years. Never. The space between us and those distant regions is expanding faster than light can travel. It's not that light is slow. It's that the very fabric holding us apart is stretching too fast for any signal to bridge the gap. Think of it this way. A photon leaves a distant galaxy, aimed directly at Earth. It begins its journey toward us. But with every second that passes, the space behind it expands. The distance it needs to cross doesn't shrink. It grows. The goalpost moves farther away with every step the light takes. Eventually, the photon gives up. It will never arrive. We will never see that light. This means something far more unsettling. Entire civilizations could exist out there right now, and we are forever cut off from them. A species could transmit radio signals toward us with perfect clarity. We will never hear them. We could broadcast our greatest achievements, our art, our science. They will never receive them. We don't just live in different regions of space. We live in causally disconnected universes, separate bubbles of reality that will never touch, never communicate, never know each other exists. And it gets worse. The expansion isn't just continuing, it's accelerating. Galaxies we can see today will eventually cross a boundary, a cosmic horizon beyond which they vanish forever. Their light will redshift, stretching into wavelengths we cannot detect. Then they'll fade. Gone. In roughly 150 billion years, every galaxy we can currently observe, except for those gravitationally bound to us, will disappear beyond this barrier. Imagine astronomers billions of years from now, looking up at the night sky. They'll see something we can barely fathom, a universe containing only the Milky Way, Andromeda, and perhaps a few dozen smaller galaxies. Everything else, the billions of galaxies we see right now, will have evaporated into the cosmic dark. Those future observers might conclude that this handful of galaxies represents the entire universe. They'll never suspect that once, in a rare cosmic epoch, the sky was full. We are living in a golden age, and we don't fully appreciate it. Right now, in this moment in history, we can see the universe. We can observe 13.8 billion years of cosmic history. We can watch galaxies being born. We can measure how fast space itself is stretching. We have telescopes revealing the early universe. This window won't stay open forever. The accelerating expansion will slam it shut, erasing the evidence. But here's the thing. Even with all our technology, even with the most powerful telescopes humanity has ever built, we're blind to most of what exists. The observable universe stretches 93 billion light years across. That's a sphere containing somewhere between hundreds of billions and possibly trillions of galaxies, countless stars, planets beyond counting. The number is so large that our brains struggle to process it. Yet this entire cosmic sphere, everything we can possibly see or ever measure, represents only a fraction of reality. It's just the part we can observe. The universe itself is larger, potentially vastly larger, maybe infinite. The evidence suggests space is geometrically flat. Imagine drawing parallel lines across the cosmos. They never meet. Draw a triangle on a cosmic scale. Its angles still sum to 180 degrees. Euclidean geometry works, and if space is flat and extends infinitely in all directions, then the universe has no edge, no boundary. It simply continues forever. Which means beyond our observable sphere, there's more, and more, and more. For every galaxy we can see, infinite galaxies exist beyond our reach. For every star lighting up our night sky, infinite stars burn in the darkness we cannot perceive. The number ceases to be meaningful because infinity dwarfs any finite number by an infinite amount. Some cosmologists propose a different picture. A universe that's finite but unbounded, like the surface of a sphere. You could theoretically travel in a straight line through space and eventually circle back to where you started. But even in this model, the total volume is staggeringly enormous, potentially trillions of light years across, still vastly, incomprehensibly larger than what we observe. Whether the universe is infinite or merely finite, but unbounded, the same conclusion holds. Beyond our horizon lies a cosmos we cannot see. Galaxy clusters form there in the dark. Cosmic filaments, structures spanning billions of light years, stretch across distances we'll never measure. Stars ignite and explode. Black holes collide and merge. Entire universes of complexity exist in regions of space we'll never reach, can never detect, can never know. The universe is vast beyond understanding, and almost all of it is hidden from us, separated by an ever-widening gulf of expanding space. We catch glimpses of one tiny corner during a brief cosmic moment. And then, as the universe accelerates away, the darkness reclaims the sky. Imagine standing at the edge of a cliff. You can see the landscape stretching out before you. Forests, mountains, rivers. But beyond that horizon, the land continues. You know it does. Yet no matter how hard you look, you cannot see it. Somewhere out there, entire civilizations might exist, following laws of nature completely foreign to anything we know. This isn't a thought experiment about Earth. This is the reality of our universe. Here's the unsettling truth. We live inside a cosmic bubble of visibility. Everything we know, every star we've charted, every galaxy we've photographed, every law of physics we've discovered, exists within a sphere called the observable universe. And beyond that sphere, things are happening that we will never, ever see. Let's start with what we actually know. Scientists build knowledge on a simple process. Observe the world, develop a theory to explain it, test that theory relentlessly, and it works spectacularly. General relativity predicted gravitational waves a century before we detected them. Quantum mechanics continues to astound us with its accuracy. These theories have been verified thousands of times within the bubble we can observe. But here's the question that keeps cosmologists awake at night. Do those laws apply everywhere else? We assume they do. It's called the cosmological principle, and it sounds reasonable. The universe, when you zoom out far enough, looks basically the same everywhere. On the largest scales, matter is distributed uniformly. Galaxies spread out in roughly equal densities across cosmic space. Our region, we think, is utterly typical. Nothing special about it at all. But think about what we're doing. We're taking observations from one small patch of space and assuming they describe the entire cosmos. We're assuming the laws we've discovered through telescopes in our little corner apply to regions we can literally never observe. That's not science in the traditional sense. That's faith. wrapped in the language of symmetry. What if we're wrong? What if, beyond our horizon, the universe is radically different? What if the constants we treat as immutable, the strength of gravity, the mass of an electron, the speed of light, are actually different out there? What if entire forms of matter and energy, stranger than anything we've imagined, dominate regions we can never reach? Some physicists take this to its logical extreme. They propose the multiverse. According to certain models of cosmic inflation, our Big Bang wasn't the only Big Bang. Imagine an infinite cosmic foam bubbling endlessly. Each bubble is a universe. Each one experienced its own explosive beginning. Some inflated rapidly, like ours did. Others inflated slowly. And crucially, each bubble evolved independently, with its own rules. In one bubble, perhaps gravity is 10 times stronger than it is here. In another, it's a tenth as strong. In yet another, the weak nuclear force operates differently. The constants are dialed to different settings, like tuning an instrument. We exist in this particular bubble, this universe, with these laws, precisely because it's tuned right for us. Carbon formed, stars ignited, life emerged. Other bubbles might be utterly sterile, their parameters so hostile that atoms never form complex structures. We can't prove any of this. We can't disprove it either. These ideas hover at the boundary between physics and pure speculation, addressing questions that might be fundamentally impossible to answer through experiment. But there's something else we know with absolute certainty. Our observable universe is not all that exists. The universe extends beyond our horizon. Somewhere out there, space keeps going. Whether it's infinite or finite, we don't know. Whether it's uniform or radically different from place to place, we don't know. Whether it's a single cosmos or one bubble among countless others, we don't know. And here's where it gets truly strange. Every location in the universe has its own observable universe. Stand anywhere, on Earth, in the Andromeda Galaxy, in the most distant galaxy we've ever detected, and look around. You'll see a sphere of galaxies stretching to your cosmic horizon. The light from those galaxies had time to reach you since the Big Bang began. Beyond that horizon, galaxies exist. You just can't see them. Their light hasn't arrived yet. But now imagine standing somewhere else, a galaxy 46 billion light-years from Earth. From that vantage point, you'd see a completely different sphere. Galaxies visible from our perspective would be beyond that distant horizon. Meanwhile, galaxies invisible to us would be crystal clear from there. Every observer, everywhere, gets their own view of the cosmos. This creates genuinely bizarre situations. Take two galaxies separated by 90 billion light-years. From their own perspectives, they can't see each other. They're in what physicists call causally disconnected regions, too far apart to have influenced each other since the beginning of time. Yet from Earth, we might see both of them simultaneously, sitting in opposite directions from us. We're watching two objects that have never seen each other. They don't know the other exists. Or consider this. There's a galaxy sitting right at our cosmic horizon. Light from that galaxy has been traveling for 13.8 billion years, and it's just now arriving at our telescopes. But from that galaxy's perspective, Earth is at their cosmic horizon. Our light is just now reaching them too. We're seeing them as they were in the ancient past. They're seeing us as we were in the ancient past. We're observing each other's ghosts, separated by billions of years of silence. The universe, it turns out, is far stranger than our telescopes can reach. There are places where space exists, where time flows, where potentially anything could be happening, and we are forever barred from knowing. We live in a cosmos of cosmic isolation, each observer confined to their own island of visibility, unable to verify that the laws governing our pocket of reality hold anywhere else. And somehow, that makes the universe even more magnificent. Imagine standing in a vast, empty field at night. You look around, and stars surround you equally in every direction. You stand at the center of your own horizon. Now imagine everyone else on Earth doing the same thing. Each person, from their vantage point, sees themselves at the center of the sky. They're not wrong. Neither are you. This isn't confusion. It's a fundamental truth about how the universe is structured. Space has no center. It has no privileged location. No special place where reality matters more than anywhere else. Every point in the cosmos, from here to the farthest galaxy, can legitimately claim to be the center of its own observable universe. This is the asymmetry of observation, and it reveals something profound about existence itself. If an alien civilization exists 20 billion light years away in a distant galaxy, they're looking at their cosmos right now and seeing the exact same thing we see. Patterns. The same cosmic web structure. The same microwave background radiation fossil from the Big Bang. But here's the twist. The specific galaxies they catalog? Completely different from ours. Their deep space surveys reveal objects we'll never see. Their most distant galaxies are unknown to us. We live in overlapping but separate observable universes, each one real, each one complete from the perspective of those living within it. This raises a haunting question. Could we ever talk to them? Theoretically, yes. Imagine we somehow detected a signal from a civilization 20 billion light years away. We send a message back into the cosmic void, 20 billion years later. Long after Earth is gone, long after our sun has died, that message arrives. They read it. They respond. And 20 billion years after that, their reply reaches us. 40 billion years for a single conversation. But it's possible, except when it isn't. If that civilization exists 50 billion light years away, communication stops being theoretical. It becomes impossible. Not because we're not trying hard enough, not because our technology isn't advanced enough, but because of something more fundamental. Space itself is expanding faster than light can cross it. Their region of reality lies beyond our cosmic horizon, the boundary where light itself cannot bridge the gap. Our signals race outward at the fastest speed the universe allows, yet they never arrive. They fall further away with each passing moment. We are permanently, absolutely isolated from them, and they're isolated from us. This limitation doesn't just apply to radio signals or spacecraft. It applies to everything. Every particle, every photon, every gravitational wave, any event occurring beyond that cosmic horizon cannot affect our region of space. Not today, not tomorrow, not ever. These distant civilizations might as well exist in separate universes. They might as well not exist at all from our perspective, because they have zero influence on our world. Yet they face identical constraints. They cannot observe us. They cannot reach us. They cannot be touched by anything happening in our region. We exist in mutually exclusive observable universes. Real places where real physics happens, connected only by the mathematics of relativity, isolated by the vast expansion of space itself. The full universe likely contains countless such spheres, each one centered on a different observer, each one revealing a different subset of cosmic reality. And each observer would be justified in asking, what does my universe mean? What is my place in all this? Then the James Webb Space Telescope looked up, and everything changed. What scientists found wasn't just shocking. It was humbling in the most profound way. The universe is far larger than we thought. And when I say larger, I don't just mean in total extent, though that's true. I mean populated, filled, crowded with galaxies beyond anything we predicted. The old estimates suggested 200 billion galaxies in the observable universe. Webb suggested closer to 10 trillion. That's 50 times more galaxies than we thought existed. Each of those galaxies contains billions, sometimes trillions of stars. Each of those stars likely hosts planets. The numbers cease to be numbers at some point. They become abstractions. Your brain cannot process 10 trillion of anything. The Milky Way, our galaxy, the vast river of light that has captivated human imagination since we first looked up, is not vast anymore. It's average, typical, one among 10 trillion others, most of which we'll never see. And Earth, our blue marble, our pale blue dot, it orbits an average star, average in size, average in age, average in every way that matters. That average star sits in an average galaxy, in an average region of space. Nothing about our location screams special. We're not in the galactic center. We're not in an unusual structure. We're not in an unusually large cluster. We're thoroughly, completely, measurably average. This is the culmination of a journey that began centuries ago. Copernicus showed us we orbit the sun, not the other way around. That was hard to accept. Earth moved from the center of everything to just another planet. Then astronomers showed us the sun is ordinary, one star among hundreds of billions in the Milky Way. Our whole world suddenly seemed provincial. Then came the discovery that the Milky Way is one galaxy among many. Then many meant billions. Now many means trillions. With each discovery, humanity got smaller. With each observation, we moved further from the cosmic spotlight. We're not the center of our solar system. We're not the center of our galaxy. We're not even in a special galaxy. We're not in an unusually large cluster. We're average. Completely, utterly average. But here's what's remarkable. This realization doesn't diminish us. It liberates us. It expands us. Because if trillions of galaxies exist, each hosting billions of stars and countless planets, the sheer mathematics of probability screams a single conclusion. We're probably not alone. The cosmos is too vast for Earth to be the only place where life emerged. The numbers don't allow it. Somewhere, in some distant, observable universe that will never touch ours, life might be looking up at its own sky, wondering the same thing we wonder, asking the same question we ask. What does it all mean? And are we truly alone? The answer, written in the language of statistics and cosmic scale, is almost certainly no. We're alone in our bubble, yes, but the universe contains far too many bubbles to remain isolated. Life, somewhere, is almost certainly looking back. Picture this. The universe is probably teeming with life. Not just here. Not just in our corner of the cosmos. Billions or trillions of civilizations might have emerged wherever chemistry permitted it, wherever evolution took hold. Life itself, intelligence itself, these probably aren't rare cosmic accidents. They're likely the inevitable consequence of a universe saturated with possibility. But here's the cruel irony. We are completely alone. Not because other civilizations don't exist, but because the distances between us are so catastrophically vast that we might as well inhabit separate universes entirely. The universe is 93 billion light years across, just in the part we can see. And that's only the observable universe. Beyond that edge, space continues, perhaps infinitely. Civilizations might be out there right now, desperately trying to reach across the cosmic dark, their signals dissolving into nothing long before they could ever reach us. We could be surrounded by neighbors, yet forever trapped in isolation. The James Webb Space Telescope has shown us just how profound this isolation truly is. Every deep field image reveals thousands of galaxies scattered across the void, each one separated by millions or billions of light years, each one containing billions of potential worlds where life could have emerged. We can see these distant galaxies now. We can study them. We can map their light and decode their secrets, but we cannot visit them. We cannot speak to anyone who might live there. That gulf, that unbridgeable distance, defines the human condition more completely than almost anything else. We occupy one planet, circling one star, in one galaxy, among 2 trillion others in the observable universe alone. And yet, this isn't a story of insignificance. It's the opposite. This is our home, our origin point, our irreplaceable context. In an incomprehensibly vast cosmos, we're privileged to live in an era when we can finally see the true scale of it, when we can understand our place within it, when we can marvel at how precious and improbable our tiny corner of reality actually is. But the universe contains wonders even more extreme than distant galaxies. At the heart of some galaxies burns a light source so intense, so overwhelmingly powerful, that it outshines every single star in that entire galaxy combined. These objects are called quasars. They are the brightest continuously shining objects in the universe. A single quasar can emit more light than 1 trillion stars like our sun. 1 trillion. Not in a year, not in a million years. Right now, constantly. A quasar's power source is almost inconceivable. A supermassive black hole consuming matter at a catastrophic rate. As gas spirals inward toward the event horizon, friction generates temperatures in the millions of degrees. This superheated maelstrom radiates energy across the entire electromagnetic spectrum. Visible light, ultraviolet, X-rays, radio waves, all screaming outward in a torrent of pure power. The energy output is so staggering that it dwarfs the combined light of hundreds of billions of stars, all compressed into a region smaller than our entire solar system. And here's the problem. These quasars shouldn't exist. We've known for decades that supermassive black holes lurk at the centers of galaxies. But building a black hole massive enough to power a quasar should take billions of years. It's a process so slow, so gradual, that it requires cosmic time on an almost unimaginable scale. Yet when Webb pointed its instruments at the early universe, when it looked back to the cosmos less than 700 million years old, a cosmic infant, it found quasars already blazing away, already impossibly massive, already unimaginably bright. One quasar detected by Webb proved so luminous that scientists initially suspected an error in their data. This single object blazes with the luminosity of 600 trillion suns. 600 trillion. More energy than our entire galaxy produces, concentrated into a space perhaps a few light months across. Think about that for a moment. The light we see from this quasar today has been traveling through space for over 13 billion years. During that entire journey, 13 billion years of travel through the cosmic void, this object has continued to radiate in all directions. Only an infinitesimal fraction of that energy happens to stream toward Earth. The total energy this quasar has released into the cosmos since the universe began is almost incomprehensible to human minds. Yet we can still detect it. We can still see it, across a distance that would take light itself longer than the entire age of human civilization to traverse. This ancient light finds us, whispers to us of a universe far stranger and more extreme than we ever imagined. Quasars serve another purpose too. Their intense light acts like a cosmic flashlight, illuminating the gas clouds suspended between them and Earth. In that light, we read the chemistry of the early universe. We decode the history of how galaxies formed. We glimpse the conditions of creation itself. The universe is bigger, more complex, more magnificent than we ever imagined. And somehow, against all odds, we're here to witness it. Imagine you're trying to map a vast, invisible city in complete darkness. You can't see the buildings themselves, but you notice that light passing through certain regions flickers in peculiar ways. Those flickers tell you something is there and tell you what it's made of. This is exactly what astronomers do with quasars. When light from these cosmic lighthouses travels billions of light years toward us, it doesn't journey through empty space. It passes through vast clouds of intergalactic gas scattered across the universe. And when that light reaches us, we can read the story written in its broken pieces. The gas has absorbed specific wavelengths, leaving dark lines like fingerprints in the quasar's spectrum. These absorption features are a gift. They reveal the composition of the gas, its temperature, and crucially, its location. By studying many quasars shining in different directions, astronomers have done something remarkable. They've reconstructed the three-dimensional architecture of the entire universe. The cosmic web emerges from the data. Filaments where gas clusters densely together, showing up as strong absorption signatures. Voids between them, where almost nothing exists, barely dimming the light at all. The universe's true skeleton has become visible. But here's the thing about quasars. They don't last forever. A quasar is a phase, a violent, brilliant, temporary phase in a galaxy's life. At the center sits a supermassive black hole, millions or billions of times the mass of our sun, and it's actively feeding. Material spirals inward at incomprehensible speeds, releasing energy that outshines entire galaxies. The quasar blazes like a cosmic searchlight, but eventually, the fuel runs out. The gas is either consumed or violently expelled. The engine sputters and dies. The black hole remains, dormant and dark, waiting in the galactic center for new material to stumble into its grasp. Our own galaxy experienced this. Billions of years ago, the supermassive black hole at the heart of the Milky Way was not quiet. It was ravenous. Our galaxy shone as a quasar, brilliant and violent. And then, like all quasars, it faded. Now, that same black hole sits largely dormant, only occasionally flaring when an unlucky star wanders too close or a gas cloud tumbles inward. We live in the quiet aftermath of an ancient explosion. The James Webb Space Telescope is changing everything we thought we knew about when these monsters woke up. Every new quasar web discovers in the distant universe light that has traveled for over 13 billion years to reach us, pushes back the timeline of when supermassive black holes first became active. The data tells an unsettling story. These black holes grew faster than our models say they should have. They became massive in an era when the universe was barely a billion years old. The pieces don't fit together yet. The mystery deepens, and quasars hold another superpower: visibility across the cosmos. A galaxy billions of light years away might be too faint to detect, lost in the cosmic glare. But a quasar? A quasar announces itself. It shines so brilliantly that we can spot it across nearly the entire observable universe. Quasars are markers, beacons. They define the frontier of space itself, the farthest reaches we can see and understand. But the universe contains wonders beyond individual quasars. When galaxies collide, the results are even more spectacular. Picture two vast cities, each containing hundreds of billions of stars, clouds of gas, and invisible halos of dark matter, hurtling toward each other at millions of miles per hour. They're on a collision course that can't be avoided. When they meet, everything changes. You might expect chaos, stars slamming into stars, a universe-ending catastrophe. But the universe is mostly empty, incomprehensibly empty. The stars themselves are so far apart that when two galaxies crash through each other, the stars simply pass through, like two swarms of gnats passing through the same space. Direct collisions between stars are vanishingly rare. Gas is different. The gas clouds from the two galaxies can't pass through each other harmlessly. When they collide head-on at tremendous velocities, shockwaves ripple through the compressed gas. Temperatures spike. Pressures become unimaginable. And then something extraordinary happens. The compression triggers a cosmic baby boom. Thousands, millions, sometimes billions of new stars ignite simultaneously. The collision zone blazes with the light of newborn stellar populations, a burst of creation born from violence. The James Webb Space Telescope captured this process in action. A galaxy merger called ARP 107 shows two galaxies mid-collision, a large spiral galaxy, its elegant arms being torn apart, is being invaded by a smaller elliptical intruder. The impact has created brilliant knots of newborn stars, visible as bright blue regions in ultraviolet light. In Webb's infrared view, they glow red, their light stretched and shifted by the expansion of space itself. The forces at work during a merger are almost unimaginable. Gravity doesn't just pull galaxies together. It warps space itself. Stars and gas are stretched into long, elegant streamers that extend hundreds of thousands of light years from the main galactic bodies. These tidal tails twist through space like cosmic ribbons. Eventually, they fall back inward. But during the merger, they create some of the most visually striking structures in the universe. Simulations reveal what happens next. When two galaxies of similar size collide, the organized spiral structure of at least one galaxy is destroyed. The neat, rotating disks are torn apart. Gradually, over millions of years, the merger debris settles into a new configuration, an elliptical galaxy, smooth, featureless, round. A phoenix born from the ashes of two colliding worlds. In this way, the universe constantly remakes itself. Quasars map its vast structure, revealing the cosmic web across billions of light years. Supermassive black holes grow and eventually quiet. Galaxies collide and merge. Structure emerges. The cosmos evolves, and we, living inside one of these evolving systems, are only now learning to read the story written across the universe. Right now, two titans are locked in a cosmic death spiral. Our Milky Way and the Andromeda Galaxy are hurtling toward each other at 250,000 miles per hour. And in about 4 billion years, they will collide. This isn't a sudden catastrophe. It's a slow-motion catastrophe. A gravitational ballet that will take several billion years to complete. The two galaxies won't just smash together once. They'll make multiple passes, gradually spiraling inward, losing energy with each encounter, until they finally merge into something entirely new. When that happens, Earth's night sky will transform beyond recognition. Andromeda will swell larger and larger as it approaches, eventually consuming vast swaths of the heavens. During the merger itself, newly formed star clusters will ignite across the darkness like a fireworks display written in the language of creation. And in the end, the two galaxies will fuse into a single, massive elliptical galaxy. Some astronomers playfully call it Milky Way. But here's what's fascinating. This won't be unusual at all. The universe's most violent construction project. The James Webb Space Telescope has been peering back toward the beginning of time, and what it's found is shocking. In the very early universe, when it was less than 1 billion years old, galaxies were already colliding with each other, and they were doing it constantly. Back then, the cosmos was smaller and denser. Galaxies crowded together like rush hour commuters. Collisions weren't rare events. They were inevitable, frequent, relentless. And here's the real revelation. These mergers might explain one of astronomy's deepest mysteries. Astronomers have discovered galaxies at the edge of the observable universe that are impossibly massive, far larger than they should be if they had simply grown through steady, gradual star formation. How did they get so big so fast? The answer? They cheated. They didn't grow one star at a time. They grew by consuming their neighbors. Massive galaxies bulked up by merging with other galaxies, accumulating their stellar populations in catastrophic collisions. It was cosmic cannibalism on a scale that reshaped the universe itself. As time passed, the merger rate declined. The universe expanded. Galaxies drifted farther apart. Collisions became less frequent. And in the far distant future, as dark energy continues to drive galaxies apart, mergers will become increasingly rare. Cosmic events will have to study in the fossil record of ancient light. Yet every massive elliptical galaxy we see today tells the same story. They're all products of cosmic violence. Their smooth, featureless appearance, that bland uniformity astronomers spent decades trying to understand, isn't the result of peaceful, orderly growth. It's the scar tissue of collision. When two galaxies merge, the chaos of their encounter erases any organized structure. Stars that once orbited in orderly disks are scattered into random paths. The organized spiral arms, the neat rings, the elegant structure, all of it gets obliterated and replaced by gravitational chaos. Yet mergers do something even more unexpected. They reshape how stars are born. Sometimes a collision triggers a furious burst of star formation, as compressed gas ignites into stellar nurseries. But sometimes the merger does the opposite. It shuts down star formation entirely. The collision heats the gas to temperatures so extreme that atoms can't collapse into new stars. The very thing that should create life instead sterilizes the cosmos, when gravity becomes a lens. But there's another side to cosmic collisions and massive galaxies. A phenomenon so strange and beautiful that even Einstein predicted it before humanity ever witnessed it. Imagine this. A massive galaxy sits between us and a distant light source. The galaxy's gravity is so intense that it warps the fabric of space-time itself around it. Light from the distant object travels through space in a straight line, as far as light can tell. But the path it follows isn't actually straight. Space itself is curved, and light, being bound to follow the geometry of space, curves with it. From our perspective, it looks like the light's path has been bent, deflected. The massive galaxy has become a lens, distorting and focusing the light from objects behind it. This is gravitational lensing, and it's one of the universe's most elegant demonstrations of general relativity made visible. Most of the time, this lensing effect creates something subtle, an arc of light or multiple images of the same distant object scattered around the massive foreground galaxy. But sometimes, when the alignment is absolutely perfect. When a distant galaxy, a massive foreground galaxy, and Earth line up with almost unimaginable precision, something extraordinary happens. The lensed light forms an Einstein ring. Every photon from the distant galaxy that passes on one side of the massive foreground object gets bent toward us. The same happens on the other side, and on the other side, and the other side. Light arrives from all directions around the lensing galaxy, creating a perfect ring of light, a halo of bent space-time made visible. Now, here's the thing. That ring isn't actually circular. It's a sphere. We see it as a circle because we're viewing a three-dimensional effect projected onto our flat, two-dimensional field of view. If you could move to the side, if you could view it from above or below the alignment, you'd see it as elliptical, warped by perspective. Einstein rings are extraordinarily rare. They demand nearly perfect alignment between three objects separated by billions of light years. The universe would have to place them in the exact right positions, at the exact right angles from our vantage point. Most lensing events create partial arcs or scattered images instead. Complete rings are statistical miracles. But when they do form, they're not just beautiful, they're powerful tools. Scientists use Einstein rings to measure the mass of the lensing galaxy with unprecedented precision. The amount of light bending depends directly on how much mass is doing the bending. A heavier galaxy deflects light more dramatically. A lighter galaxy deflects it less. By studying the ring's geometry, astronomers can weigh entire galaxies, measuring their mass across billions of light years with nothing but light and mathematics. The Webb Space Telescope recently captured one of the most stunning Einstein rings ever photographed. A perfect ring of light surrounding a massive foreground galaxy, a prediction made by Einstein nearly a century ago, finally made visible in all its glory. And it reminds us of something profound. The universe isn't just a collection of random objects drifting through empty space. Everything is connected. Light bends around matter. Galaxies spiral together through gravitational attraction. Stars scatter into chaos when their galaxies collide. The cosmos is a web of relationships, written in the language of gravity and geometry. In 4 billion years, our galaxy will learn this lesson firsthand. Imagine you're looking at the universe, and a massive galaxy sits directly between you and an even more distant one. Something remarkable happens. The nearby galaxy's gravity warps space-time itself, bending the light from the far galaxy like a lens, creating a glowing ring of magnified starlight we call an Einstein ring. But here's what makes this truly extraordinary. By measuring that ring's size and shape, astronomers unlock a hidden secret of the cosmos. They can weigh the invisible. When astronomers measure an Einstein ring's radius and compare it to the known distance of the background galaxy, they calculate the total mass of the foreground object, everything visible and everything we cannot see. These measurements reveal something profound. Dark matter doesn't stop at the edges of galaxies. It extends far beyond, forming massive halos that envelope entire systems. The Einstein ring's size tells us exactly how far those invisible halos reach into space. What emerges from this analysis is a portrait of cosmic architecture. Dark matter forms a rough sphere around every galaxy, its mass concentrated densely at the center and gradually fading as you move outward. It's like an invisible fortress surrounding each island of stars. Webb captured one such ring recently, a galaxy from 13 billion years ago, so distant and ancient it would be invisible to us. But a foreground galaxy, only 4 billion light years away, sits perfectly between us and this relic of the early universe. The foreground galaxy's gravity magnifies and brightens the distant one, transforming it from a faint smudge too dim to study into a brilliant ring where scientists can now read its secrets. They measure spectral features. They calculate star formation rates. What was once impossible becomes possible. This is nature's gift. Massive galaxies acting as natural telescopes. These cosmic magnifying glasses boost the light from objects behind them, pulling distant galaxies into clarity. Without lensing, the James Webb Space Telescope would simply see darkness where those high redshift galaxies exist. The light is too faint, the distance too great, but lensing brings them into view, and the effect scales dramatically. Galaxy clusters, cosmic cities containing hundreds or thousands of galaxies, along with superheated plasma and dark matter, create even more violent gravitational distortions. Background galaxies get stretched into long arcs. Some appear multiple times as light takes different paths around the cluster's massive bulk. The resulting images look alien. Galaxies warp into crescents and elongated streaks, twisted and magnified beyond recognition. Webb scientists know this secret, so they deliberately point the telescope at these known massive clusters. They use the clusters as cosmic lenses, magnifying background galaxies that would otherwise remain invisible. This strategy has revealed some of the faintest and most distant galaxies ever detected. Objects that should be invisible are now observable. The most extreme lensing amplifies background objects by factors of 10 to 100. This transforms the impossible into the observable. But what these magnified images reveal is something darker. A dramatic story of cosmic destruction. When a galaxy falls into a massive cluster, it doesn't gently drift into orbit. It plunges through the cluster at millions of miles per hour. During this violent passage, something catastrophic occurs. The galaxy enters a hostile environment that will tear away everything it needs to survive. Between the galaxies and a cluster lies what seems empty, but isn't. It's filled with plasma, ionized gas superheated to tens of millions of degrees. This intergalactic medium is thin by Earth standards, but on cosmic scales it has weight and substance. When a galaxy tears through this inferno at extreme speeds, something brutal happens. Imagine sticking your hand out of a moving car window. The air pressure pushes against your hand. You're not moving through stationary air. The air is pushing back at you. Galaxies experience the same force. The hot plasma exerts what astronomers call ram pressure, and it's relentless. The pressure strips the cold gas from the galaxy, gas that the galaxy desperately needs. Observations show the evidence plainly. Long tails of material streaming behind galaxies as they plunge through clusters. These tails extend for hundreds of thousands of light years, containing enough gas to build millions or billions of new stars. But these stars are never born. The gas is abandoned in the cluster, left behind to disperse into the cosmic void. Without gas, the galaxy dies, not as an explosion, but as a slow fade. Star formation requires cold gas that can collapse under gravity. No gas means no new stars. No new stars means the galaxy ages, its light dimming, its future erased. Once vibrant and fertile, the galaxy becomes a graveyard of old suns, slowly drifting through the cluster as a fossil of what it once was. Imagine a thriving city, bustling with life, new buildings rising constantly. Then one day, something catastrophic happens. The supply lines are cut off. Resources stop flowing in. The construction cranes fall silent. Eventually, all the old buildings crumble. What's left is a ghost town, a monument to what once was. This isn't just a metaphor. It's happening right now, across the universe, to billions of galaxies. When a galaxy's gas gets stripped away, something extraordinary happens. Star formation doesn't just slow down, it stops. Completely, within a few 100 million years, the creative engine of the universe shuts off. The existing stars keep shining, sure. They continue their lonely vigil in the darkness. But when they die, nothing replaces them. No newborns to take their place. The galaxy undergoes a cosmic transformation. That brilliant blue spiral, the signature of a young, fertile galaxy, fades away. What emerges is a red, dead elliptical or lenticular galaxy, a galactic graveyard. The James Webb Space Telescope has caught this process in the act. It's called environmental quenching, and the evidence is overwhelming. Here's the stunning part. Location matters. It matters a lot. Place a galaxy in isolation, and it churns out several entire stellar masses worth of new stars every single year. That same galaxy, the identical twin, falls into a dense cluster. Its star formation rate plummets to zero. Not to nearly zero, to zero. The difference is that dramatic. But the brutality isn't distributed equally. Small galaxies are particularly vulnerable. Think of it this way. Massive galaxies have deep gravitational wells, powerful enough to cling to their gas like a desperate grip. Small galaxies? They have weak gravity, fragile, defenseless. When a small galaxy passes through the violent core of a cluster, ram pressure, the cosmic equivalent of a hurricane wind, tears away its entire gas supply in a single passage. The galaxy becomes red and dead, forever locked into its aging population of ancient stars. Webb captured something haunting. A galaxy nicknamed the Jellyfish Galaxy. As it plunges through its host cluster, ram pressure rips long, ghostly tentacles of gas and stars trailing behind the main body. For a brief, heartbreaking moment, stars still form inside these tentacles. Then the gas dissipates completely. The galaxy leaves behind a trail of star clusters, like breadcrumbs marking its path toward oblivion. A literal trail of death. But ram pressure isn't the only killer. Tidal forces join the assault. The combined gravity of the cluster and neighboring galaxies pulls and tears at the infalling galaxy. Outer stars get stripped away. The galaxy becomes smaller, more compact, more broken. Over billions of years, magnificent spiral galaxies, the kind we might call beautiful, get reduced to tiny, dense elliptical remnants, transformed beyond recognition. And there's one more executioner: starvation. In isolation, galaxies continuously drink in fresh material from the cosmic web, those vast filaments of gas that thread through the universe. This cosmic nutrient flow replenishes the gas burned up by star formation. It's a renewable resource, but in clusters, the intergalactic medium becomes too hot, too energetic to be captured. The supply line is severed. New gas never arrives. Here's what makes this truly cosmic in scale. Roughly half of all galaxies in the universe live in groups or clusters. That means environmental effects are sculpting the destinies of billions upon billions of galaxies. This isn't a minor phenomenon. This is one of the dominant forces shaping cosmic evolution, and the consequences ripple across all of time itself. The early universe was chemically simple, brutally simple. Hydrogen, helium. That was it. Two elements born in the first minutes after the Big Bang. Everything else, carbon, oxygen, nitrogen, iron, silicon, magnesium, the entire periodic table of elements that makes up you, me, and everything around us, came later. Much later. These elements were forged inside massive stars. When those stars died in spectacular supernovae, they scattered their creations across the cosmos. Webb has witnessed this cosmic enrichment process by peering at galaxies across vast distances and different epochs. Nearby galaxies, their light reveals spectral lines from dozens of elements. The full periodic table is written in their radiation. But look at the most distant galaxies, the ones we're seeing as they were over 13 billion years ago, and you find something different. Primarily hydrogen and helium. Only traces of heavier elements. Only faint whispers of complexity. This pattern tells an epic story. The universe has been teaching itself chemistry over billions of years. Astronomers call this metallicity, and yes, they use the term metals to mean anything heavier than helium, even though elements like oxygen and carbon aren't metals at all. The terminology stuck, and now it defines cosmic history. Low metallicity means a young, simple universe. High metallicity means an ancient universe, enriched by countless stellar furnaces. The first stars formed from pure hydrogen and helium. They lived fast. They died young. Their explosions scattered the heavy elements they'd created. The next generation of stars inherited this enriched material. They produced even more complexity. And so the cycle continued, generation after generation, building the chemical foundations for planets and life itself. Every atom in your body, every carbon atom in your DNA, every iron atom in your blood came from a star that lived and died billions of years ago. You are, quite literally, made of stardust, and the universe is still in the process of creating that stardust, one stellar forge at a time, until environments like galaxy clusters silence those forges forever. Imagine the cosmos at its birth, a realm of almost perfect simplicity. Hydrogen, helium, a few traces of lithium. That's it. Everything else, the iron in your blood, the oxygen in your lungs, the calcium in your bones, didn't exist yet. But then something extraordinary happened. The first stars ignited, massive, brilliant, short-lived furnaces burning so intensely that they forged new elements in their cores. When they died, and they died young, these stellar titans exploded, scattering their creations across the galaxy. They added heavy elements to the cosmic gas. And then came the next generation of stars, born from this slightly enriched material. They too created new elements, died, and enriched the gas further. Generation after generation, star after star, each one leaving its chemical fingerprint on the universe. We can actually read this fingerprint. Light traveling from distant galaxies carries a story written in invisible handwriting. Absorption and emission lines, patterns of light and shadow at specific wavelengths. Oxygen creates one signature. Carbon creates another. Measure how strong these lines appear compared to hydrogen, and you know exactly what elements fill that distant galaxy's gas. And here's what the data reveals. The universe has been getting heavier. Galaxies born when the universe was just 700 million years old, those at redshift 8, contain heavy elements at only 2% of the levels we see in nearby galaxies today. By the time the universe reached 1.5 billion years old, redshift 4, that number jumped to 20%. At redshift 2, about 3 billion years after the Big Bang, galaxies had accumulated 50% of today's heavy element content. And now, 13.8 billion years later, we've reached where we are. This wasn't inevitable. Dense regions where stars form rapidly became metal-rich quickly. Sparse regions where star formation crept along remained pristine, metal-poor, ancient. When galaxies collided and merged, the violent collision triggered massive bursts of star formation, and suddenly, Heavy elements accumulated at breakneck speed. The most metal-poor galaxies Webb has observed are cosmic museums, windows into the universe's youth, before significant chemical processing. Their composition matches almost perfectly what Big Bang nucleosynthesis theory predicted. These are the closest things we have to the universe's original recipe. But here's the crucial detail. Even in these metal-poor systems, some elements appear more abundant than others. Oxygen builds up faster than iron. Why? Because different kinds of stars produce different elements. Massive stars that burn out in a few million years forge mostly oxygen. Smaller stars that burn slowly for billions of years produce more iron. By measuring the ratio of oxygen to iron, astronomers read the history of star formation written in chemistry. This is why it matters so profoundly. A rocky planet cannot form from hydrogen and helium alone. Life, at least the kind we understand, cannot exist without carbon, nitrogen, oxygen, phosphorus, and dozens of other heavy elements. Our Sun is a third-generation star, minimum. It formed from gas already enriched by earlier stellar generations, gas that contained silicon, iron, oxygen, and all the raw materials needed to build Earth and everything living on it. Every atom in your body, except for hydrogen, was created inside a star, forged in nuclear furnaces millions of times hotter than the Sun's core, and then scattered across space by a stellar explosion. You are made of stardust, literally, but more than that. You are a fossil record of the universe's chemical evolution. The heavy elements in your body arrived here only because billions of generations of stars came before you, lived, died, and enriched the cosmos. That few percent of heavy elements, the difference between a universe of pure hydrogen and our chemically complex cosmos, made all the difference. It made planets possible. It made chemistry possible. It made life possible. It made you possible.